For centuries, the idea that planets might exist beyond our solar system was nothing more than speculative thought. While it seemed likely that other worlds existed in the vastness of space, no solid evidence could confirm it. Telescopes were simply unable to capture these distant objects clearly, with stars only appearing as faint, unmoving dots in the sky. It wasn't until the late 20th century that astronomers developed more advanced tools capable of detecting even the slightest changes in starlight. With these new instruments, the invisible began to emerge. The first confirmed exoplanet discovery happened in 1992, but it came as a surprise. Instead of orbiting a regular star, these planets were found circling a pulsar, a highly magnetic, rotating remnant of a supernova. The 3 exoplanets were detected through tiny changes in the timing of the pulsar's pulses. This discovery was groundbreaking. Planets surviving in such a harsh, radiation-filled environment seemed to challenge everything scientists knew about planet formation. Yet, the discovery was undeniable and opened the door to further exploration. The next major discovery came in 1995, when Michel Mayor and Didier Queloz discovered 51 Pegasi b, a massive planet orbiting very close to its star, which was completely unexpected. With a mass similar to Jupiter and an orbit of just 4 days, it defied existing theories, which predicted gas giants could only exist in far-off orbits. The discovery was made using the radial velocity technique, which measured the subtle wobble of the star caused by the planet's gravity. This finding marked the beginning of a new era. Within a few years, more exoplanets were discovered using similar methods, challenging the notion that Earth was unique or the center of the universe. Scientists began to wonder not only if other planets existed, but how many might be habitable, resemble Earth, and perhaps even harbor life. What began as an outlier discovery has since turned into one of the most exciting and vibrant areas of modern science, with thousands of exoplanets catalogued. Over the next few years, methods like transits and gravitational microlensing helped expand our understanding. The transit method in particular became crucial in identifying the sizes and orbits of these distant worlds. Every new planet discovered sparked greater interest, both in the scientific community and the public, and led to more investment in space telescopes like Kepler. As technology progressed, scientists began to shift focus from the discovery of massive extreme planets to smaller, more Earth-like ones. The variety of exoplanets found was staggering. Planets with retrograde orbits, exotic weather systems, and even evaporating atmospheres showed that planetary formation could take many unexpected paths, quite different from those in our solar system. What had once seemed like exceptions turned out to be common, and the familiar models were only one possibility in a sea of options. The next challenge became understanding whether any of these planets could support life. The concept of a habitable zone emerged, guiding many searches, but this raised new debates. A planet being habitable doesn't necessarily mean it can support life or be pleasant for humans. Yet the discovery of planets with even slight Earth-like features sparked incredible excitement. Every advancement in technology led to deeper investigations, with the Kepler Space Telescope ushering in an era of rapid discovery. In just a few years, over 2,000 exoplanets were identified. Kepler not only confirmed that planets are common, but it also revealed that many star systems contain multiple planets in tight orbits, which is quite different from our solar system structure. This discovery fueled the imagination, suggesting that our galaxy could be filled with planetary systems, some possibly more stable and diverse than our own. Today, scientists study exoplanets in greater detail than ever before, even those hundreds of light years away. We can now estimate their mass, size, atmospheric composition, and even surface temperature. It's an impressive achievement, considering that most of these planets haven't been directly observed. Instead, we detect their presence by analyzing the effects they have on their stars or the light they filter when they pass in front of them. This ability to interpret tiny shifts in light has revolutionized our understanding of these distant worlds. Exoplanet discovery has also led to significant advancements in various scientific fields. New technologies in instrumentation, artificial intelligence, spectroscopy, and even astrobiology are now integral parts of this evolving field. The study of exoplanets has become a highly interdisciplinary effort, involving physicists, engineers, chemists, biologists, and even philosophers. The search for new worlds has become not just about finding other planets, but about understanding the deeper meaning of our place in the cosmos. Despite all the progress, exoplanet detection is still a science of limits. Many small planets remain beyond current detection capabilities, and the faint atmospheres of some worlds require next-generation telescopes. However, the pace of discoveries continues to increase, and new techniques emerge every decade. What was once thought to be invisible is now routine, and the idea that other worlds exist has shifted from a hypothesis to a statistical certainty. There are billions of exoplanets in our galaxy alone. Each new discovery brings new questions, reigniting old ones. Where are the planets with life? How many are truly Earth-like? Are we alone in the universe? While science doesn't yet have the answers, it now has the tools to search for them with unprecedented precision. The TRAPPIST-1 system, discovered in 2017, brought even more excitement, revealing not one but 7 Earth-sized planets, orbiting a cool dwarf star just 40 light-years away. One of these planets, TRAPPIST-1e, stood out because it lies in the habitable zone, the region around a star where temperatures are right for liquid water to exist. This planet, similar in mass and size to Earth, is considered one of the most promising candidates in the search for habitable worlds outside our solar system. The star it orbits is small, cold, and red, only 9% the size of our Sun, which means the habitable zone is very close to the star. All 7 planets in the system are closer to their star than Mercury is to our Sun, creating complex orbital interactions. Despite this close proximity, TRAPPIST-1e could still maintain temperatures suitable for liquid water due to the star's low energy output. The planets in the TRAPPIST-1 system are likely tidally locked, meaning one side constantly faces the star while the other remains in permanent darkness. This brings up intriguing questions about the climate of TRAPPIST-1e. Could there be a temperate zone between the 2 extreme hemispheres? Climate models have been run to explore different possibilities, and many suggest that if the planet has an atmosphere, it could help balance the heat and moderate the temperature extremes. This makes understanding the planet's atmosphere essential when assessing its habitability. The James Webb Space Telescope was partly designed to investigate atmospheres of exoplanets like TRAPPIST-1e. By analyzing starlight that passes through the planet's atmosphere during a transit, scientists can detect gases like carbon dioxide, methane, and water vapor. While the data is still in its early stages, some potential atmospheric compositions have already been ruled out. Each new piece of information helps fine-tune the models, getting us closer to understanding what might really exist on this distant world. The density of TRAPPIST-1a suggests it has a rocky composition, similar to Earth and possibly an iron core. This supports the idea that the planet could have active geodynamics, which are necessary for maintaining a stable atmosphere over time. Moreover, due to the compact nature of the system, TRAPPIST-1a likely experiences continuous gravitational interactions, generating internal heat, another potential factor for habitability. While there is no direct evidence of life or liquid water on the planet, it has quickly become a symbol in the search for Earth-like worlds. Its proximity to Earth has made it a key target for future missions and observations. If we ever manage to capture direct images of exoplanets, TRAPPIST-1a will undoubtedly be one of the first. For many, this planet represents the hope of discovering a cosmic twin to Earth. The fact that there are 7 planets in the TRAPPIST-1 system, with 3 or 4 potentially in the habitable zone, reminds us that life could exist in environments very different from our own. Stars like TRAPPIST-1, which are small and cool, were once thought unlikely to support life, but now they are prime research targets. Their stability and longevity suggest that if life were to arise, it could have plenty of time to evolve. In that context, TRAPPIST-1e is just one possibility among many. Studying such a distant planet presents enormous challenges. Even with the best telescopes, all we can do is measure tiny fluctuations in light and interpret them through theoretical models. Science often moves between what we can see and what we can infer, turning faint data into plausible images of entire worlds. TRAPPIST-1e, in a sense, is a scientific construct, built from numbers, spectra, and hypotheses. With each new measurement, part of the mystery fades away, only for more questions to arise. If it has an atmosphere, how did it form? Could water exist on its surface, or is it trapped underground? Is the planet tectonically active, or is it frozen in silence? These questions continue to drive research, and TRAPPIST-1a has expanded the boundaries of what we can imagine about distant worlds. Beyond its scientific value, TRAPPIST-1a also holds symbolic significance. In a universe filled with billions of stars, the discovery of a planet so similar to Earth, close in size and potentially in conditions, forces us to reconsider our place in the cosmos. TRAPPIST-1a has become an icon, featured in research papers, documentaries, and even science fiction. It embodies the notion that something out there could resemble Earth, not just in a vague sense, but with concrete details like mass, orbit, and composition. The search for planets like TRAPPIST-1a is also changing the direction of space exploration. Instead of focusing solely on Mars or Jupiter, we are now looking deeper into the cosmos. Future missions are already being planned to study these distant worlds in more detail, and perhaps, one day, to send interstellar probes to explore them. While we can't yet reach TRAPPIST-1a, the planet is already shaping the decisions we make here on Earth. Even without direct proof of life or images, TRAPPIST-1a plays a pivotal role in showing that potentially habitable worlds do exist, and that they are measurable and studyable. Kepler-186f, discovered in 2014 by the Kepler Space Telescope, was the first Earth-sized exoplanet found within the habitable zone of its star. It orbits a red dwarf star, Kepler-186, located about 500 light-years away. With a diameter just slightly larger than Earth's, Kepler-186f became a key example of rocky planets orbiting cool stars, which are far more common in the galaxy than stars like our Sun. Its orbit lasts 130 days, and it receives about 1/3 of the sunlight that Earth gets. Because its star is smaller and redder than our Sun, its habitable zone is much closer to the star. Kepler-186f sits near the outer edge of this zone, meaning its surface temperature is highly dependent on the planet's atmosphere, which has not yet been detected. If Kepler-186f has an atmosphere similar to Earth's, it might sustain liquid water. Otherwise, it could be a frigid world with temperatures below freezing. However, it's still unknown whether Kepler-186f even has an atmosphere. The transit method, which was used to detect it, can tell us the planet's size but not its mass or density directly. Statistical models suggest that Kepler-186f is likely rocky, but this is still unconfirmed because we don't have radial velocity measurements. Without these measurements, we can't determine the planet's surface gravity or internal composition. Due to its distance and the faintness of its star, it's unlikely that we will be able to study its atmosphere with current instruments. Telescopes like James Webb would struggle to analyze atmospheres of small, distant planets orbiting dim stars. For now, Kepler-186f remains an important target, though limited in the amount of observational data we have. It continues to serve as a milestone in our understanding of habitable exoplanets. The Kepler-186 system contains at least 4 other planets, all of which orbit closer to the star and are outside the habitable zone. This suggests that compact multi-planet systems are common around small stars. The system's stability aligns with planetary formation simulations around red dwarfs, meaning these planets may have formed in close orbits from the beginning. The presence of multiple planets provides opportunities to study orbital interactions and long-term system evolution. Kepler-186f is particularly interesting because it lies near the lower mass limit for retaining an atmosphere around low-luminosity stars. If the planet has been exposed to intense ultraviolet radiation from its star, it may have lost much of its original atmosphere. However, this depends on the star's activity history and the presence of a planetary magnetic field, neither of which have been observed in this case. Atmospheric erosion plays a crucial role in determining the habitability of planets around red dwarf stars. Kepler-186f, for example, receives only about 32% of the sunlight Earth gets. Thermally, this places it in a range similar to Mars. However, the actual temperature depends heavily on the planet's atmosphere and surface properties. If the planet's surface has a high albedo reflectivity, it would reflect more sunlight, causing it to cool. On the other hand, if the albedo is lower and greenhouse gases are present, they could trap enough heat to keep temperatures in an Earth-like range. Kepler 186, Eph's position near the edge of the habitable zone, makes it a valuable subject for testing the limits of habitability. Scientists use advanced climate models to simulate how the atmosphere would behave, even in the absence of direct data. These models help us predict how the planet's climate could be affected by factors like its orbital tilt, rotational speed, and the activity of its host star. Kepler 186f, therefore, acts as a test case for these simulations. In addition to climate, the possibility of oceans on Kepler 186f raises further questions about its internal processes. To sustain liquid water for billions of years, the planet would need a geological cycle to recycle minerals and stabilize its atmosphere, including its levels of carbon dioxide. This process relies on tectonics, volcanism, and internal heat sources, like radioactive decay. While these processes are inferred from other planets of similar size and density, they cannot yet be confirmed for Kepler 186f. The fact that its star is a red dwarf offers an intriguing possibility, a lifespan that could extend for trillions of years. This would increase the chances of long-term climate stability, as long as the planet can retain a viable atmosphere. However, red dwarfs are also known for intense magnetic activity in their early stages, with frequent flares that could compromise a planet's habitability. The exact age of the Kepler 186 system remains uncertain, which makes it difficult to fully understand its evolutionary history. Despite these challenges, Kepler 186f has already made significant contributions to exoplanet science. It has not only opened the door to studying planets around red dwarfs, but also demonstrated that small planets can be detected with high precision. Its size, orbit, and star are all relatively common characteristics, suggesting that many more similar planets are waiting to be discovered. This solidifies the idea that Earth-like worlds are not as rare as once thought. The transit method is one of the primary ways we detect exoplanets. This method involves observing a star's brightness as a planet passes in front of it, blocking a small fraction of its light. These tiny changes, often less than 1%, can be recorded using photometers with high precision. The timing and frequency of these dimming events allow scientists to determine the planet's orbital period and the size of its orbit. The depth of the transit provides direct information about the planet's size. The bigger the planet, the more light it blocks. The shape and duration of the transit also give clues about the planet's orbital angle and the presence of moons or rings. For the transit method to work, the planet's orbit needs to be aligned with Earth's line of sight, which only happens in a small fraction of planetary systems. However, by combining transit data with the planet's mass, measured using the radial velocity method, scientists can estimate its density and infer whether it is rocky, gaseous, or a mixture of both. This combination of methods has allowed for the creation of a new classification system based on a planet's mass and radius, revealing an astonishing variety of exoplanets. By observing transits at different wavelengths, scientists can also analyze the atmospheres of these planets. The Kepler Space Telescope, designed specifically to use the transit method, observed over 150,000 stars simultaneously during its primary mission. This allowed it to detect thousands of exoplanet candidates, many of which were later confirmed with other instruments. Kepler's findings confirmed that planets are common and that systems with multiple planets in tight orbits are frequent. One of the major advantages of the transit method is that it also allows scientists to study exoplanet atmospheres using transmission spectroscopy. During a transit, some of the star's light passes through the planet's atmosphere and is altered by the gases it contains. By analyzing this altered light, scientists can identify molecules like water vapor, methane, carbon dioxide, and ammonia. This process requires extremely precise equipment, but it offers invaluable information about the composition of exoplanetary atmospheres. The method can even detect the presence of exocomets, rings, and moons, though with more difficulty. Irregularities in the transit profile can indicate complex structures around the planet, such as evaporating atmospheres. These unusual profiles are detectable only with very sensitive telescopes and depend on the contrast between the planet and its star. While the transit method relies heavily on orbital alignment, it still remains one of the most effective ways to study exoplanets. To compensate for its limitations, a large number of stars must be observed for extended periods. This is why missions like Kepler and TESS were designed with wide fields of view and long durations. The longer a star is observed, the greater the chances of detecting planets with long orbits, such as Earth analogues. The precision required to detect transits is incredibly high, on the order of thousandths of a magnitude. As a result, instrumental fluctuations, stellar activity, and background noise can all interfere with the data, requiring advanced statistical processing and machine learning techniques to extract accurate information. Additionally, some phenomena like eclipsing binaries can mimic planetary transits, making it crucial to rigorously validate each detection. Despite these challenges, the transit method remains one of the cornerstones of exoplanet research. Not only does it allow us to discover new planets, but it also provides detailed insights into their properties. Combined with other methods, it gives us a comprehensive view of planetary systems and is one of the most productive techniques for characterizing exoplanets. The radial velocity method, also known as the Doppler method, detects exoplanets by observing slight shifts in a star's light spectrum caused by the gravitational pull of an orbiting planet. As the planet moves around its star, it causes the star to wobble slightly, creating a periodic shift in the star's light, blue when it moves toward us, and red when it moves away. These shifts indicate the presence of a companion planet and allow astronomers to calculate the planet's orbital characteristics. This method does not detect the planet directly, but rather measures the star's motion in response to the planet's gravity. The size of the wobble depends on the planet's mass and the shape of its orbit. Larger planets, particularly those close to their stars, cause stronger and more detectable wobbles. By measuring these wobbles over time, astronomers can determine the planet's orbital period, minimum mass, and distance from its star. This method is especially sensitive to large planets, like hot Jupiters, that orbit close to their stars, and these were among the first exoplanets discovered using this technique. Recent improvements in instrumentation have made it possible to detect smaller planets with weaker signals, even down to the size of super-Earths. In favorable cases, this advancement has expanded our ability to discover and study a wider range of exoplanets. Modern spectrographs have become extraordinarily advanced, able to detect even the slightest shifts in velocity, as small as just 1 meter per second. By plotting these shifts over time, we create radial velocity curves that reveal the motions of stars. When these patterns are smooth and sinusoidal, it typically indicates a planet's orbit is circular. The shape of this curve can also tell us about the orbit's eccentricity. Variations in the curve's amplitude help estimate the planet's mass. However, there's a catch. This method only provides a planet's minimum mass, because the angle at which the planet's orbit tilts is usually unknown unless we combine this data with transit observations. When combined with transit data, the picture becomes clearer, allowing us to determine the planet's actual mass and size. Not only does the Doppler technique uncover planets, but it can also help us study multi-planet systems. By analyzing how the radial velocity signal changes over time, astronomers can identify multiple planets with different orbits. But this is no easy task. Distinguishing between overlapping signals from different planets requires complex statistical models and extensive long-term observation. In systems where planets' orbits are in resonance, the gravitational forces between the planets can cause small but detectable deviations from simple sinusoidal motion. To capture these variations, spectrographs must remain stable over long periods, which is a challenge. Instruments like HARPS and espresso are some of the most precise spectrographs available, capable of detecting planets that resemble Earth, orbiting relatively quiet stars. To achieve such precision, these instruments require temperature regulation, vibration isolation, and specialized calibration systems to minimize any instrumental drift. Thanks to these advancements, we've been able to push the boundaries of radial velocity surveys, allowing us to study smaller planets and those with longer orbital periods. Radial velocity is one of the few methods that can directly confirm the mass of a planet, an essential step in understanding its composition. A planet with the same radius could either be a gas giant or a rocky world, depending on its mass and density. Without knowing the mass, identifying the planet as one or the other based solely on its size is virtually impossible. This is why ground-based radial velocity follow-ups are often used to verify discoveries made via space-based transit observations. While the method works best with bright stars that rotate slowly and have low magnetic activity. When stars are too active or rotating too quickly, they can create noise that drowns out the planetary signal. As a result, new techniques like machine learning and statistical filtering have been developed to remove stellar interference and clarify the planetary signals. One major limitation of the radial velocity method is that it requires repeated observations over long periods, which can take years, especially when hunting for planets with longer orbital periods, like Jupiter analogues. It's also difficult to detect planets around low-mass stars or distant stars due to weaker spectral lines. Despite these challenges, radial velocity remains essential for characterizing planets and serves as a crucial confirmation tool for planets discovered through other methods. When a transit signal is ambiguous or might be caused by an eclipsing binary system, radial velocity measurements can definitively confirm or rule out the presence of a planet. As sensitivity continues to improve, astronomers aim to detect true Earth analogues orbiting Sun-like stars. To achieve this, they'll need precision down to 10 centimeters per second, a goal that is still out of reach but within sight, with upcoming spectrographs and missions expected to make this possible. Now let's explore another groundbreaking method: gravitational microlensing. This technique allows us to detect exoplanets by using Einstein's theory of general relativity. In this method, a foreground star acts as a gravitational lens, bending the light from a more distant background star. If the foreground star has a planet, the planet's gravity can cause a tiny brief distortion in the light curve, revealing its presence. Unlike radial velocity or transit methods, microlensing doesn't rely on the light from the star itself. Instead, it can detect planets around stars that are either too faint or too distant for traditional techniques to detect. This makes it an invaluable tool for studying planetary systems thousands of light years away, especially those in the galactic bulge. Microlensing also helps us discover planets in wide orbits, including Jupiter analogues, and even rogue planets that drift through interstellar space. Microlensing events are rare and unpredictable, requiring constant monitoring of millions of stars. Most surveys focus on regions of the Milky Way, where the likelihood of stars aligning is greatest. When an event does occur, the brightness of the background star increases for several days or weeks, depending on the masses and velocities of the objects involved. The anomalies caused by planets last only a few hours or days. By analyzing these distortions, astronomers can estimate a planet's mass and its distance from its host star. However, because microlensing events are so complex and often lack follow-up data, estimating the exact properties of the planet remains challenging. Despite these hurdles, microlensing is an invaluable tool for detecting low-mass planets that would otherwise be difficult to find. It excels at detecting planets located far from their stars, in cold regions beyond the snow line, and has provided the only evidence so far for the existence of rogue planets. These planets, unbound to any star, float freely through the galaxy. Microlensing doesn't favor large, short-period planets like other methods. Instead, it provides a unique view of the planetary population, revealing planets that might resemble our own solar system's architecture. This makes it a critical technique for demographic studies of planetary systems, offering insights into how planets form and evolve. Both ground-based and space-based observatories, like the Optical Gravitational Lensing Experiment, OGLE, and the MOA microlensing observations in astrophysics, have led the field for years. The upcoming Nancy Grace Roman Space Telescope, formerly known as WFR's, is poised to revolutionize microlensing by performing observations from space with unprecedented precision and stability. However, there are significant drawbacks. Microlensing events are non-repeating, meaning once the alignment ends, no further data can be gathered from that particular event. This makes long-term observations difficult. Additionally, microlensing is more effective in densely populated star fields like the galactic bulge, but much less useful in the sparse regions of our solar neighborhood. While the method provides valuable insights, its geographical bias means most discoveries occur in parts of the galaxy far from our own environment, limiting our ability to directly relate them to our solar system. Despite these limitations, microlensing remains an essential tool in the quest to understand exoplanetary systems. It offers unique access to planetary types that no other method can detect as effectively, helping us piece together the rich diversity of planets that populate the galaxy. One such planet is K218b, located about 124 light-years away in the constellation Leo. This super-Earth exoplanet has captured the attention of scientists after water vapor was detected in its atmosphere. This discovery, made with the Hubble Space Telescope, marked the first time water vapor was confirmed on a potentially habitable zone exoplanet. K218b's size, about 8.6 times Earth's mass and 2.6 times its radius, suggests it's likely not a rocky planet like Earth, but rather a gas-rich world. Still, its location within the habitable zone of its star means it could potentially support liquid water, depending on its atmospheric conditions. However, further study is required to determine if K218b could truly support life. This discovery has sparked a renewed interest in planets around red dwarf stars, which are much dimmer than our Sun. While these planets might be too hot or cold to support life, K218b's position in the habitable zone provides hope that it could host an environment conducive to life, despite its considerable differences from Earth. Models suggest that K218b likely has a significant atmosphere composed of volatile gases, possibly with a thick layer above an ocean-covered surface. Some simulations point to it being a water world, an exoplanet with a vast global ocean beneath a hydrogen-rich atmosphere. The thickness and pressure of this atmosphere are key to understanding its surface conditions and whether it could support life. With a bulk density lower than Earth's, K218b's mass and radius support the idea of a thick atmosphere or internal water layers, making it a prime example of a sub-Neptune planet. Sub-Neptunes are quite common in exoplanet surveys, but absent in our solar system. These planets typically have a rocky or icy core surrounded by a gas envelope, and their thickness can vary significantly. K218b's position on the spectrum of exoplanets makes it an important target for understanding these types of worlds. However, determining the habitability of K218b is complicated by its host star, Merdwarfs. The type of star K218b orbits are known for their intense magnetic activity, including flares that emit high levels of ultraviolet and X-ray radiation. Such flares can strip away a planet's atmosphere or make the surface uninhabitable. Fortunately, K218b's host star appears relatively quiet for its class, and simulations indicate that its thick atmosphere could offer the necessary protection. Long-term observations will be crucial in determining if this environment can sustain the kind of complex chemistry needed for life. Recent data from the James Webb Space Telescope (JWST) adds more intrigue to K218b's atmospheric makeup. The detection of methane and carbon dioxide in its atmosphere supports the presence of a secondary, more evolved atmosphere. These molecules are not typically found in gas giants, indicating a level of chemical complexity that could suggest interactions between the surface and the atmosphere. While these findings aren't definitive proof of habitability, they place K218b higher on the list of exoplanets worth further study. One of the intriguing aspects of K218b's atmosphere is its potential for regulating climate. On Earth, processes like the carbonate-silicate cycle help stabilize global temperatures over geological timescales. However, such processes might not function on water worlds or sub-Neptunes due to the extreme pressures or the lack of land. This could limit the potential for climate feedback systems, although alternative mechanisms may be at play. To understand this more thoroughly, scientists will need to develop more detailed models tailored to thick atmosphere exoplanets like K218b. Looking ahead, future studies, particularly those using the JWST, will refine our understanding of K218b's atmospheric structure and composition. The telescope's instruments are capable of distinguishing between clear atmospheres, cloudy ones, and those with photochemical hazes. These observations will help us determine whether the water vapor detected on K218b is part of a shallow haze layer or whether it's indicative of a deeper ocean-compatible atmosphere. K218b represents an important bridge between rocky Earth-like planets and gas-rich Neptune-like worlds. It offers scientists a rare opportunity to study the conditions that might allow for habitability, even if the planet doesn't quite fit the traditional Earth analog mold. By focusing on planets with intermediate masses, researchers can broaden their understanding of the different types of planetary environments that may exist in the universe and how common conditions suitable for life might be. These findings will also improve our models of planet formation, particularly in red dwarf systems. Despite its thick atmosphere and relatively low mass, the presence of water vapor, methane, and carbon dioxide makes K218b one of the most promising sub-Neptunes discovered so far. While it may not be habitable in the same way as Earth, it represents a crucial step toward understanding what makes a planet capable of sustaining life. The ongoing study of K218b will help refine our understanding of the boundaries that define habitability in non-terrestrial atmospheres. Now let's shift our focus to the TRAPPIST-1 system, located about 40 light-years away in the constellation Aquarius. This system contains 7 Earth-sized planets orbiting an ultra-cool red dwarf star. What makes this system so exciting is that several of these planets are within or near the habitable zone, where temperatures could potentially allow liquid water to exist. All 7 planets have radii within 15% of Earth's densities that suggest they are rocky, similar to Earth. The star itself is only about 9% the mass of our Sun and is much cooler, emitting most of its light in the infrared. The planets, labeled TRAPPIST-1b through TRAPPIST-1ha, orbit very closely to their star, so closely, in fact, that the entire system fits within the orbit of Mercury. Despite the close orbits, these planets maintain stable orbits due to orbital resonances, which likely played a significant role in stabilizing the system during its formation. The orbital periods of these planets range from 1.5 to 20 Earth days, meaning their years are measured in days, not months. 3 of these planets, TRAPPIST-1F and G, fall within the habitable zone, suggesting that they could potentially harbor surface water. However, whether they are truly habitable depends on several factors, including their atmospheric composition, ability to retain an atmosphere, and the radiation environment of their host star. The low luminosity of the TRAPPIST-1 star means that planets in close orbits can maintain temperate climates, as long as they have the right kind of atmosphere to trap heat. The planets are likely tidally locked, meaning one side always faces the star, while the other remains in perpetual darkness. This could lead to extreme temperature contrasts between the day and night sides, unless the planet's atmosphere can efficiently redistribute heat. Scientists have been closely studying the TRAPPIST-1 system with the Hubble and James Webb Space Telescopes. The goal is to detect key atmospheric components, such as carbon dioxide, methane, and water vapor, during planetary transits, when light from the host star passes through the planet's atmospheres. Early data from Hubble suggests that the planets likely don't have puffy, hydrogen-rich atmospheres, which increases the likelihood that they have thinner, more Earth-like atmospheres. The compact arrangement of the TRAPPIST-1 system offers scientists a unique opportunity to study planet formation and evolution in such a densely packed environment. By analyzing the densities of the planets, scientists can make inferences about their internal structures. Some planets may have more iron in their cores, while others may have thicker ice layers or volatile-rich compositions. The mutual gravitational influences between the planets also provide valuable data on their internal structures, helping scientists understand their geology through transit timing variations. One challenge for the TRAPPIST-1 system is the star's magnetic activity. Despite being cooler and smaller than our Sun, TRAPPIST-1 emits strong flares and high-energy radiation, especially during its early stages. This radiation could erode the atmospheres of nearby planets, particularly if they lack protective magnetic fields. However, it's believed that some of the planets could still retain substantial atmospheres, depending on their initial conditions. The architecture of the system suggests that all 7 planets likely formed further out and then migrated inward. This migration could explain their close orbits and the resonant relationships between them. Simulations are currently underway to test this migration model and to better understand how water-rich planets might form beyond the snow line and remain hydrated during inward migration. The TRAPPIST-1 system provides an unparalleled opportunity to study multiple Earth-sized planets within a single system. The JWST will continue to refine our models of their atmospheres, providing crucial data on their climate, surface chemistry, and the impact of stellar radiation on these small rocky planets. As one of the most studied exoplanetary systems, TRAPPIST-1 offers a rare chance to understand the diversity of rocky planets around low-mass stars. Finally, let's revisit the concept of the habitable zone, often referred to as the Goldilocks zone. This is the region around a star where the conditions are just right for liquid water to exist on a planet's surface. This zone is defined by the amount of radiation a planet receives from its star, depending on the star's luminosity and spectral type. For Earth-like planets, the habitable zone is the sweet spot where conditions are just right for water to exist in its liquid form. However, habitability depends on more than just distance from a star. Factors such as atmospheric composition, planetary mass, and surface pressure play a critical role. The boundaries of the habitable zone are not fixed. They shift depending on the characteristics of the star. Around a Sun-like star, the habitable zone usually extends from about 0.95 to 1.37 astronomical units. But for red dwarfs, which have lower luminosity, the habitable zone is much closer, often within 0.1 AU. This proximity leads to a variety of effects, including tidal locking, magnetic activity, and potential issues with orbital stability. Therefore, the concept of the habitable zone must be adjusted based on both the star's environment and the planetary conditions. Even if a planet is located within the habitable zone, it doesn't guarantee that it has liquid water or a temperate climate. For instance, Venus is within our Sun's habitable zone, but its thick CO2-rich atmosphere causes a runaway greenhouse effect, making it uninhabitable. Similarly, a planet on the outer edge of the zone may still be too cold to support liquid water without a sufficient amount of greenhouse gases. The planet's atmospheric composition, surface reflectivity, and geothermal heat all influence its actual surface conditions. There are different models to define the habitable zone. The conservative model assumes Earth-like atmospheric conditions and water-carbon chemistry, setting strict boundaries. More optimistic models expand this zone to include planets that might harbor subsurface oceans or employ alternate greenhouse mechanisms. Another model, known as extended habitability, takes into account factors like a planet's eccentricity or the warming influence of nearby gas giants and tidal heating. Planets around near dwarfs face unique challenges. Their proximity to the star increases the likelihood of tidal locking, flare exposure, and magnetic erosion. Yet their long lifespans could allow ample time for biological development, assuming the planet can retain its atmosphere. Simulations suggest that thick atmospheres or oceanic worlds could buffer these effects, but the data is still limited. The presence of an atmosphere is crucial to determining a planet's habitability. Without atmospheric pressure, water cannot stay in a liquid state. It would either freeze or vaporize. Spectroscopic observations of transiting planets are used to analyze their atmospheres. The detection of molecules like water vapor, carbon dioxide, or methane may suggest greenhouse dynamics that could help sustain liquid water on the surface. Mass and size are also important factors. A planet that's too small might lack the gravity to hold onto an atmosphere, while a planet that's too large could develop a thick, crushing envelope like Neptune's. The inner edge of the habitable zone is defined by the point at which a planet loses its water due to runaway greenhouse effects. The outer edge is defined by the amount of stellar energy required to prevent the planet from freezing over. These thresholds are modeled through sophisticated 3D climate simulations that consider cloud formation, surface types, and atmospheric circulation. Differences in a planet's rotation, axial tilt, and surface composition add further complexity to the analysis. Planets in binary or multiple star systems may experience shifting or dynamic habitable zones. The gravitational influences from multiple stars can change the planet's exposure to radiation over time, meaning the habitability of such planets becomes a variable condition. In these systems, habitability depends on orbital resonances and long-term stability. Climate models for such planets require more advanced simulations to account for the unique dynamics at play. Astronomers have shifted toward referring to planets within the habitable zone as potentially habitable. This phrasing reflects the uncertainty involved, particularly when detailed atmospheric data is unavailable. While missions like Kepler and TESS have discovered many such planets, very few have been thoroughly studied. Only a small fraction are currently within reach of detailed atmospheric analysis. Expanding the definition of habitability beyond just surface water includes considering subsurface oceans, atmospheric biospheres, or tidal heating environments. Moons like Europa and Enceladus in our solar system serve as analogues for potential non-surface habitability. Exomoons and water-rich planets may fall into these categories, but they challenge the traditional habitable zone framework. In summary, while the habitable zone is a useful starting point, it's an incomplete metric for determining whether a planet can support life. It lays the groundwork for identifying potential habitable environments, but must be considered alongside other planetary and atmospheric factors. Observational limitations and theoretical uncertainties mean that many planets within the habitable zone may turn out to be inhospitable, while some outside it may harbor water in non-traditional ways. The concept of habitability remains a foundation for deeper exploration and scientific discovery. Let's now look at an example of a planet undergoing extreme conditions, WASP-12b. This hot, Jupiter-type exoplanet is located approximately 1,400 light-years away in the constellation Auriga. It orbits its star at a dangerously close distance, just 0.023 astronomical units, and completes a full orbit in about 1.1 Earth days. This close proximity subjects WASP-12b to tremendous tidal forces and intense stellar irradiation. As a result, the planet's atmosphere is being gradually torn apart by the star's gravity, and the planet is slowly being consumed. The tidal forces have caused WASP-12b to become distorted, giving it an oblate, egg-like shape. Unlike the nearly spherical gas giants in our solar system, WASP-12b's shape reflects the massive gravitational differential between its near and far sides. These forces also generate significant heat within the planet, potentially contributing to the expansion of its atmosphere. The outer layers of the atmosphere are so extended that they spill beyond the planet's Roop limit, the region where the planet's gravity can no longer hold onto material. As a result, material from the atmosphere is forming an accretion disk around the host star. Observations in ultraviolet and optical wavelengths show evidence of metal ions and hydrogen streaming from the planet. This mass transfer not only erodes the planet, but also affects the star's spectral lines and brightness variations, enriching the star with heavy elements as the planet is consumed. Estimates suggest that WASP-12b could lose up to 10 billion tons of mass per year. If this rate continues, the planet could be completely evaporated or reduced to a rocky core within a few 100 million years. The interaction between the planet and its star provides a fascinating case study in planetary death and atmospheric escape under extreme conditions. WASP-12b's dayside temperature exceeds 2500 K, hot enough to dissociate molecules and emit detectable thermal radiation. Infrared observations reveal a significant temperature gradient between the day and night sides, suggesting that heat transport within the planet's atmosphere is inefficient, possibly due to a shallow atmosphere or strong radiative cooling. WASP-12b is also thought to be in a decaying orbit. The tidal forces that distort its shape also cause the planet to lose orbital energy, gradually spiraling inward toward its star. If this trend continues, the planet's demise will be accelerated. Long-term monitoring of transit timing variations can help confirm this hypothesis, offering rare and valuable data for modeling planetary dynamics. The host star of WASP-12b is a late F-type star, slightly more massive and hotter than the Sun. Its high-energy radiation plays a role in accelerating the planet's atmospheric escape. Stellar magnetic activity may also contribute, though the specific mechanisms are still being investigated. Observations across multiple wavelengths from UV to infrared are essential to fully understand the interaction and its impact on the planet's atmosphere. WASP-12b offers a rare glimpse into the final stages of a gas giant's evolution. While hot Jupiters are commonly discovered, few show such advanced stages of tidal disruption. Studying WASP-12b helps refine our understanding of the lifespans and fates of short-period gas giants and how they influence their host stars. Its atmospheric data also provide valuable benchmarks for comparative exoplanetology, especially regarding atmospheric loss and tidal interactions. This planet is not the only one undergoing such a fate, but it is one of the most extreme and best observed examples. Future missions, such as Ariel and the JWST, will continue to analyze its spectrum in greater detail, providing even more insights into its demise. The Kepler Space Telescope, launched by NASA in 2009, marked a monumental turning point in the search for exoplanets, with one goal in mind: determining how common Earth-like planets are in our galaxy. Kepler revolutionized our understanding of planetary systems. It worked by continuously observing the brightness of over 150,000 stars, searching for the smallest dips in light caused by planets passing in front of their host stars, a method known as the transit technique. Kepler's precise photometry allowed it to detect incredibly small variations in light, often less than 0.001%, forming the foundation of modern exoplanet science. Kepler's continuous, uninterrupted observations over long periods of time allowed it to detect planets with long orbital periods, including those within their stars' habitable zones. Although many early discoveries focused on hot Jupiters, Kepler's data expanded the scope to smaller planets like super-Earths and mini-Neptunes. The biggest revelation was that intermediate-sized planets were far more common than previously believed, completely reshaping our understanding of planetary architectures. The mission's first major success came with Kepler-10b, the first confirmed rocky exoplanet. This discovery paved the way for future findings of planets that were close in size and mass to Earth. In 2011, Kepler-22b made headlines as the first planet found in the habitable zone of a Sun-like star. Following that, planets like Kepler-186, F and TRAPPIST-1e were discovered, further expanding our understanding of potentially habitable worlds. Kepler's discoveries led to the creation of the Exoplanet Archive, a comprehensive database cataloging planetary candidates and confirmed planets. Its data also revolutionized exoplanet demographics by offering a statistically significant sample of planets, making it possible to estimate the occurrence rates of planets based on size, orbit, and host star type. One of the most surprising findings was that small rocky planets are not just common, but especially prevalent around Mia dwarfs. Studies based on Kepler data now suggest that nearly every Sun-like star likely hosts at least one planet, transforming exoplanet science from a rare discovery field into one focused on population analysis. Kepler also provided insight into multi-planet systems with tightly packed orbits. For example, Kepler-11, which has 6 planets orbiting close to each other, demonstrated that planetary systems can remain stable even in compact configurations. These findings challenged the assumption that our own solar system was a typical example, showing that planetary systems are much more diverse than once thought. Although Kepler's mission came to an end in 2013 after a failure in its reaction wheels, it continued to contribute valuable data during the K2 mission, which began in 2014. The K2 mission focused on observing different regions of the sky in 80-day campaigns, providing new insights into planetary occurrence and variable star research. Despite being less stable, K2 continued the work of the original Kepler mission, expanding our knowledge of exoplanets in different parts of the sky. One of Kepler's major contributions was its role in understanding false positives. Some signals that appeared to be planetary transits turned out to be caused by eclipsing binary stars or instrumental noise. To address this, Kepler's team developed statistical validation tools to differentiate real planets from false candidates. These tools, now a standard in exoplanet research, are used in combination with radial velocity and imaging data to confirm new discoveries. Kepler's legacy is not just in its discoveries, but in the infrastructure and techniques it established. The photometric pipeline, light curve analysis tools, and candidate vetting procedures laid the groundwork for future missions. Public data releases from Kepler also encouraged the growth of citizen science projects like Planet Hunters, where amateur astronomers could help discover new planets missed by automated algorithms. Perhaps one of Kepler's most lasting impacts was in the field of astroseismology. By studying stellar pulsations, scientists were able to refine measurements of host star properties such as mass, radius, and age. This allowed for better estimates of planetary characteristics and helped calibrate models of stellar evolution, making Kepler an essential tool for both planetary science and stellar astrophysics. By the end of its mission in 2018, Kepler had confirmed over 2,600 exoplanets and identified thousands more candidates. It had provided the statistical framework for future missions like TESS and the James Webb Space Telescope. Kepler's discoveries also influenced the design and scope of new telescopes, encouraging the development of missions that could cover a broader range of the sky with higher cadence and more integrated methods. It became clear that space-based photometry was not just feasible but incredibly transformative. Even though Kepler is no longer operational, its data continues to be mined for new insights. Advances in machine learning and data processing have uncovered planets that were previously overlooked. Kepler's archive remains one of the most valuable datasets in astronomy, and its impact will continue to shape the field for years to come. In many ways, Kepler answered the question, are we alone, not with speculation, but with the hard data to back it up? TESS, the Transiting Exoplanet Survey Satellite, was launched by NASA in 2018 to build on Kepler's legacy with a broader, all-sky survey. While Kepler focused on a single region of the sky, TESS observes nearly the entire sky in segments, each for about 27 days. Its primary goal is to detect planets transiting bright nearby stars, ideal candidates for further study with ground-based telescopes and the James Webb Space Telescope. Using 4 wide-field cameras, TESS monitors the brightness of over 200,000 stars per sector, focusing on stars that are 30 to 100 times brighter than those observed by Kepler. This allows for more detailed studies of the planets it detects. TESS places a particular emphasis on finding small planets, such as Earth-sized and super-Earth planets, especially those orbiting M-dwarfs. These planets are excellent candidates for transmission spectroscopy and long-term monitoring, which could provide further details about their atmospheres and orbital dynamics. TESS's orbit, known as a P2 resonance orbit, allows for long uninterrupted observations while minimizing stray light and thermal fluctuations. The spacecraft's 2-year primary mission covered 85% of the sky and identified thousands of exoplanet candidates. The success of the extended mission has allowed TESS to revisit previously scanned areas for deeper coverage. TESS releases its data quickly and publicly, enabling rapid scientific analysis and fostering citizen science projects. Volunteers in projects like Planet Hunters assist in identifying transit signals that automated algorithms may have missed, leading to faster discoveries and increasing the chances of finding unusual planetary systems. Collaborations with observatories around the world allow for swift follow-up and validation of promising candidates. Unlike Kepler, which aimed for statistical completeness, TESS is optimized for finding planets that can be characterized in detail. It complements Kepler's mission by identifying targets suitable for mass measurements, atmospheric studies, and direct imaging. This makes TESS a vital part of the planetary science pipeline, feeding directly into the scheduling of follow-up observations with the JWST and other missions. TESS also monitors stellar flares, eclipsing binaries, pulsating stars, and supernovae, providing valuable time series data across many astrophysical fields. Its diverse functionality makes it one of the most versatile tools in astronomy. Some of TESS's most intriguing discoveries include TOE 700 Days, a potentially habitable Earth-sized planet, and LHS 3844b, a hot, rocky world with no detectable atmosphere. These findings highlight TESS's ability to find planets that both offer exciting potential for habitability and present extreme environments that challenge our current models of planetary formation and evolution. As TESS continues its mission, It is helping to redefine our understanding of exoplanets and their potential for supporting life. TESS focuses on the brightest and most observable exoplanets, prioritizing these over population completeness. This approach aligns with its broader mission of characterizing planetary atmospheres and identifying potential biosignatures. TESS has become a leader in exoplanet follow-up science, providing invaluable data that also supports studies of planetary dynamics. By examining transit timing variations and orbital resonances, TESS helps scientists reconstruct the evolutionary history of planetary systems. In systems with multiple planets, the data collected allows for more refined orbital models and mass constraints when combined with radial velocity measurements. This synergy of methods has deepened our understanding of planetary systems and helped push the field beyond mere detection toward a detailed characterization of planets. With every new discovery, TESS continues to advance exoplanet science into a more in-depth physical study. Its flexibility, efficiency, and compatibility with other instruments make it an essential tool in the ongoing search for nearby, observable worlds. Now let's turn our attention to the James Webb Space Telescope, JWST, which launched in 2021 and is designed to take exoplanet research to the next level. Equipped with cutting-edge infrared instruments, JWST is perfectly suited to study the atmospheres of exoplanets. Unlike its predecessor, the Hubble Space Telescope, JWST operates mainly in the infrared spectrum. This allows it to peer deeper into planetary atmospheres and uncover molecular features that were previously out of reach. Its high-resolution spectrographs, NIR-SPEC, NICAM, and MIRI, can analyze light passing through or emitted by the atmospheres of exoplanets, providing crucial information about their composition. JWST employs two primary methods to study exoplanet atmospheres: transmission spectroscopy and emission spectroscopy. In transmission spectroscopy, starlight filters through a transiting planet's atmosphere, leaving behind absorption features that reveal the presence of gases such as water vapor, methane, and carbon dioxide. Emission spectroscopy, on the other hand, examines the thermal radiation emitted by the planet itself, often during secondary eclipses when the planet passes behind its host star. Together, these techniques provide complementary insights into the planet's atmospheric composition, temperature, and overall structure. One of JWST's greatest advantages is its sensitivity to smaller planets, including super-Earths and mini-Neptunes. Previous telescopes struggled to study planets smaller than Neptune due to low signal-to-noise ratios, but JWST's large mirror and infrared optimization allow it to gather more light, enabling the detection of weaker spectral signals. This makes JWST an invaluable tool for observing planets around cool, faint M-dwarfs, where habitable zone planets are more likely to be found and studied. Early observations from JWST have already demonstrated its capabilities. For instance, data from exoplanets like WASP-39b revealed distinct signatures of water vapor, carbon dioxide, and sulfur dioxide in the planet's atmosphere. These findings showcase the precision of JWST's wavelength coverage and its ability to detect absorption bands beyond the reach of Hubble. The telescope's ability to simultaneously detect multiple molecular species is critical for understanding atmospheric chemistry and potential photochemical processes on distant worlds. JWST also provides temperature-pressure profiles of exoplanet atmospheres. By measuring brightness across various wavelengths, scientists can infer how temperature changes with altitude. This helps model atmospheric circulation, cloud formation, and energy transport between the day and night sides of tidally locked planets. Such models are crucial for understanding the climates of planets orbiting red dwarfs and the thermal structures of giant exoplanets. The telescope is particularly effective at analyzing atmospheres with low metallicity or high cloud content. JWST's instruments can penetrate deeper layers of a planet's atmosphere when clouds obscure the upper layers in optical wavelengths. This is particularly useful for planets like GJ 1214b, where previous missions found featureless spectra due to thick clouds or hazes. JWST can differentiate between cloud layers, photochemical hazes, and gas-dominated atmospheres, providing a more detailed understanding of a planet's true atmospheric makeup. JWST is also focused on studying atmospheric escape, especially for close-in exoplanets. Strong stellar radiation can strip away the upper atmosphere of these planets over time. By observing ionized species, Lyman alpha lines, and deviations in molecular abundances, JWST can detect signs of atmospheric escape. Studying these processes helps scientists understand planetary evolution, particularly for Neptune's and rocky planets on the edge of habitability. JWST's continuous wavelength coverage, from 0.6 to 28 microns, enables the detection of molecules like methane, ammonia, and ozone. These molecules are important for assessing both abiotic and potentially biotic processes. Some of these molecules, such as carbon dioxide and methane, can have both biological and geological origins, making their interpretation crucial. By comparing the ratios of these molecules, researchers can infer the dominant sources and chemical pathways active in a planet's atmosphere. Observations with JWST are scheduled around transit windows and predicted secondary eclipses. Due to the telescope's sensitivity and limited field of view, careful allocation of observing time is essential. High-priority targets include nearby rocky planets in systems like TRAPPIST-1 and K218, selected based on their brightness, transit geometry, and expected atmospheric signal. To collect sufficient data, long integration times are often required, especially for smaller planets. The telescope's pointing stability and low background noise are vital for precise photometric measurements. JWST is stationed at the Earth-Sun LOL-2 Lagrange point, where thermal and gravitational conditions are stable. Its sunshield and cryogenic systems help maintain the optimal operating temperatures required for infrared observations. These conditions minimize instrument noise and allow for extended monitoring of exoplanet systems. JWST's ability to conduct comparative planetology, studying the atmospheric properties of a wide variety of planet types, is another significant strength. By observing hot Jupiters, sub-Neptunes, and Earth-sized planets, JWST can help refine our understanding of atmospheric composition, thermal dynamics, and planetary evolution across different star systems. In summary, JWST is a game-changer in exoplanet research. It offers unprecedented access to atmospheric data, spanning a broad range of planet sizes, temperatures, and orbital distances. Its high spectral resolution and extensive infrared coverage make it the most powerful tool yet for unraveling the chemical fingerprints of distant worlds. Whether detecting biosignatures, methane, ozone, or other key molecules, JWST provides invaluable insights that will deepen our understanding of distant planets and their potential for habitability. One of the key focuses of exoplanet research is the search for biosignatures, chemical or physical indicators that suggest the presence of biological activity. On Earth, certain gases in our atmosphere are linked to biological processes. Common biosignature candidates include oxygen, O2, ozone, O3, methane, CH4, nitrous oxide, N2O, and combinations of these gases in disequilibrium. While the detection of these gases doesn't confirm life, it can indicate processes that are difficult to explain by purely abiotic mechanisms. For example, the coexistence of oxygen and methane in an atmosphere is highly unstable without ongoing replenishment. On Earth, oxygen is produced through photosynthesis, and methane comes from microbial methanogenesis. If similar imbalances were found on distant exoplanets, it could point to biological activity, though false positives remain a concern. Methane is a high-priority target in the search for biosignatures. While it can be produced biologically, it can also have geological origins, such as from volcanic activity or UV-driven photochemistry. Therefore, context is critical when interpreting methane detections. Methane paired with oxygen in the right quantities strengthens the case for life, whereas methane alone is less conclusive. Ozone is another key biosignature because it forms when UV light splits oxygen molecules, which then recombine to create O3. The presence of ozone in an exoplanet's atmosphere suggests free oxygen, which on Earth is a byproduct of biological processes. However, non-biological oxygen production via photodissociation of water or CO2 must also be considered when interpreting ozone signals. Nitrous oxide, On2O is less abundant but highly indicative of biological activity. It is produced primarily through microbial denitrification. However, detecting N2O in exoplanet atmospheres is challenging due to its weak spectral features and low concentrations. In certain atmospheric conditions, particularly around M dwarfs with low UV flux, N2O could accumulate and become detectable. The search for biosignatures requires precise measurements, as distinguishing weak spectral lines from noise and stellar variability can be difficult. Instruments like JWST, along with upcoming missions like Ariel and HabEx, will use transit and direct spectroscopy to detect biosignatures. Atmospheric modeling plays a critical role in identifying potential false positives, simulating how biosignature gases would behave under different stellar radiation and planetary conditions. Planets around quiet, nearby M dwarfs are high-priority targets for biosignature searches due to their favorable conditions for observation. And however, the activity of M dwarfs, such as flares and UV radiation, can complicate the interpretation of biosignature data. Understanding the behavior of the host star is just as important as analyzing the planet itself. In the search for biosignatures, disequilibrium chemistry, where gases exist in unstable ratios, remains one of the most promising indicators of biological activity. For example, the simultaneous presence of oxygen and methane in an atmosphere suggests active processes replenishing both gases. This disequilibrium is challenging to explain without biological mechanisms, making it a compelling signal of life. Disequilibrium chemistry, where gases coexist in unstable ratios, is an uncommon feature in abiotic systems and usually requires ongoing input from biological or unknown mechanisms. Future telescopes will target these chemical combinations as primary biosignature candidates. In addition to gaseous biosignatures, future direct imaging missions may be able to detect non-gaseous signatures, such as pigments or surface reflectance features, like the red edge found in vegetation on Earth. These detections will require extremely high spatial resolution and contrast to separate the planet's light from the overwhelming brightness of its host star. Missions like ELUVOR and HabEx are currently in the planning stages and are designed with these capabilities in mind. In exoplanet biosignature science, the focus is on gathering statistical confidence and interpreting the context behind each discovery. A single detection of a biosignature gas is rarely enough to confirm biological activity. Instead, scientists look for consistent evidence from multiple species across different lines of data and compare these results with physical models. The field is moving toward comprehensive atmospheric profiling rather than simply identifying isolated gases. This shift marks a significant evolution in the way we study exoplanets and their potential for life. One fascinating class of exoplanets under study are water worlds, planets thought to be covered by vast global oceans. These planets are believed to form beyond the snow line in their protostellar disks, where ices and other volatiles accumulate in high concentrations. As these planets migrate inward toward their stars, they can enter the habitable zone while still maintaining deep water layers. These worlds are often thought to be composed of a combination of rock, metal, water, and exotic ices in stratified layers beneath the surface. Direct confirmation of water worlds is challenging, but scientists infer their presence through bulk density measurements. Planets with radii between 1.5 and 2.5 times that of Earth, paired with relatively low densities, may suggest significant water or volatile content. Exoplanets like K218b and GJ1214b fit this profile, with spectra indicating dense atmospheres over water-rich interiors. In fact, the water content of these planets could exceed 20% by mass, vastly more than Earth's 0.02%. These theoretical models suggest that water worlds may contain a thick, high-pressure ice mantle beneath their global oceans. As you go deeper into these oceans, water would transition into exotic ice phases, such as Ice 7 or Ice X, which only occur under extreme pressure and temperature conditions, phases not naturally found on Earth. Whether these unique structures can support geologic or biological processes remains an open question. Internal heat, convection, and chemical gradients would be key factors in determining whether life could exist under these extreme conditions. The surface conditions of water worlds are heavily influenced by both their atmospheres and the type of star they orbit. A hydrogen-rich atmosphere might lead to high surface pressures and temperatures, potentially preventing the formation of traditional oceans. On the other hand, a thinner secondary atmosphere composed mainly of water vapor or nitrogen could allow liquid oceans with Earth-like characteristics. Cloud layers, albedo, and greenhouse gases all play crucial roles in regulating the energy balance and climate on these planets. One challenge in detecting oceans on these worlds is that they leave limited signatures in transit spectroscopy. While water vapor in the atmosphere may be detectable, it's not enough to confirm the presence of liquid water on the surface. To address this, scientists rely on models that combine density and atmospheric composition data to predict internal structures. For planets without solid surfaces, ocean depth estimates remain highly uncertain, ranging anywhere from tens to hundreds of kilometers. Water worlds with permanent global oceans may not have the rock-water interfaces that are critical for nutrient cycling, as seen on Earth. Without continents or tectonics, vital minerals could become trapped below dense ice layers or seafloor pressure zones. However, hydrothermal activity driven by internal heating might still create the energy and chemical gradients needed to support life. These conditions could mirror the deep oceans on Earth where life thrives despite the absence of sunlight. A key question remains whether these deep oceans can remain stable over geological timescales. Volatile loss, atmospheric escape, or photodissociation of water molecules could reduce the ocean's mass over time. However, a magnetic field, thick atmosphere, or high planetary gravity could mitigate these effects. Planetary cooling and internal differentiation would also influence the longevity and structure of these oceans. Tidal forces play a role in shaping the thermal and dynamical behavior of water worlds, particularly those in eccentric orbits, or those orbiting close-in dwarfs. Tidal heating could generate internal friction, maintaining subsurface warmth and allowing for stable liquid layers even when stellar radiation is weak, but excessive tidal heating could destabilize the oceans, potentially triggering a runaway greenhouse effect. Water worlds may not display plate tectonics like Earth. A deep ocean could act as a barrier to crustal recycling and convection. In these planets, stagnant lid tectonics or alternative mechanisms might dominate. These structural differences affect volcanic activity, atmospheric replenishment, and long-term climate regulation. The possibility of life emerging under these conditions remains uncertain, but it is something we can test through future missions. Future telescopes like the James Webb Space Telescope, JWST, and Ariel aim to refine our understanding of water worlds. Transmission spectroscopy will help detect water vapor, clouds, and other volatiles, and combined with mass radius data, this will provide better constraints on water content. Direct imaging missions may eventually detect surface glints, an optical signature of large liquid bodies. Research into water worlds is also informed by the study of icy moons and dwarf planets within our own solar system, such as Europa, Enceladus, and Ganymede, all of which host subsurface oceans beneath icy crusts. These local analogues give us valuable insight into the interior processes, chemical interactions, and energy sources that might exist on similar exoplanets. In summary, water worlds represent a distinct class of exoplanets with unique internal dynamics and the potential for habitability. While their detection relies on indirect methods, and characterization requires integrated atmospheric and structural modeling, advancements in technology are improving our ability to study these planets. As we continue to refine our tools, we will be able to test these models and better assess the prevalence of alien global oceans across the galaxy. Now turning our attention to super-Earths, rocky exoplanets larger than Earth. These planets are common targets for exoplanet surveys. Super-Earths range from 1 to 10 times the mass of Earth, and have radii up to 1.6 to 2.0 times that of Earth, depending on composition. They lie between Earth and Neptune in size, and their physical nature can vary widely. Some super-Earths are rocky with thin atmospheres, while others might have significant volatile layers or gas envelopes. Notably, super-Earths are absent from our solar system, making them a prime focus for comparative exoplanetary science. Super-Earths are the most frequently detected type of planet in exoplanet surveys. Their size and mass produce strong signals in both transit and radial velocity measurements, making them ideal candidates for detection. Kepler's data revealed that super-Earths are especially abundant around male dwarf stars and are often found in tightly packed systems, offering valuable insights into planet formation and migration processes that are not seen in our own solar system. The distinction between a rocky super-Earth and a gas-rich mini-Neptune is determined by a combination of mass, radius, and atmospheric retention. Planets with radii below 1.6 Earth radii typically have high densities consistent with rock and metal compositions, while those above this threshold tend to have lower densities, suggesting hydrogen-helium envelopes or extensive water layers. Super-Earths can have intense surface gravity, up to 3 or 4 times that of Earth, which affects atmospheric retention, surface pressure, and tectonic activity. A denser atmosphere could provide more insulation and greenhouse warming, but this may also present challenges for observations. The depth of a super-Earth's atmosphere impacts its spectral characteristics, and high pressure could limit the types of chemistry occurring on the planet's surface. Geological activity on super-Earths depends on internal heating and crust dynamics. Larger planets generally have more radiogenic heat, which could lead to longer-lasting magma oceans. Some models suggest that super-Earths may be more geologically active than Earth, with enhanced mantle convection and more vigorous plate movement. However, whether these planets display plate tectonics depends on factors like lithosphere strength, water content, and surface temperature. The presence of plate tectonics would have significant implications for climate regulation, as seen on Earth with the carbon-silicate cycle. If super-Earths exhibit similar processes, they could maintain temperate climates that allow liquid water. However, planets with stagnant lid tectonics may trap volatiles, resulting in more extreme surface environments. Atmospheric composition is crucial in determining the habitability of super-Earths. Depending on their formation history and proximity to their host star, super-Earths may have atmospheres rich in CO2, water vapor, nitrogen, or hydrogen. Hydrogen-rich atmospheres may retain heat, but could also hinder UV-driven photochemistry. A denser secondary atmosphere composed of heavier molecules would offer better prospects for habitability and biosignature detection. Super-Earths in their stars' habitable zones such as LHS 114b, 2I700d, and GLI 581d are prime candidates for future studies. These planets' surface conditions suggest that liquid water could exist, provided they have the right atmospheric conditions. To study these planets further, telescopes like JWST can observe their atmospheric absorption features during transits. This data will help constrain their greenhouse gas content and surface pressure, moving us closer to understanding the habitability of these fascinating exoplanets. When we look at super-Earths, particularly those orbiting men-dwarfs, there's a high chance of tidal locking due to their short orbits. This means one side of the planet always faces the star, while the other remains in perpetual darkness. But don't worry, this doesn't necessarily make them uninhabitable. Thanks to advanced climate models, we know that a thick atmosphere could act as a heat distributor, spreading warmth from the day side to the night side, which helps stabilize temperatures. Clouds, atmospheric circulation, and even oceans could all play a part in shaping whether these planets could support life. The combination of these factors determines how habitable the planet might be. Advanced 3D climate models are essential in simulating different scenarios and providing insights into how super-Earths behave under various conditions. Another critical factor in understanding the habitability of super-Earths is their magnetic field. Planets with larger, iron-rich cores might have more robust magnetic fields which can shield them from harmful stellar winds. This protection would be especially important for super-Earths orbiting active megageological surface. However, detecting magnetic fields in exoplanets is still challenging, as we currently rely on models and indirect data to infer their presence. These super-Earths are incredibly diverse. Some could have scorching, molten surfaces due to intense stellar radiation, while others might feature thick clouds that trap liquid water beneath. Their thermal properties are defined by the interplay of stellar radiation, albedo, the reflectivity of the planet's surface, and the depth of their atmospheres. In the future, missions aimed at studying these planets will focus on measuring surface temperatures and analyzing spectral features to better understand what they're made of. The continued exploration of these rocky planets could hold the key to understanding planet formation, internal structure, and the potential for life. Mini-Neptunes are a fascinating class of exoplanets, often larger than super-Earths but smaller than Neptune itself. They are typically between 2 and 4 times the radius of Earth and have masses ranging from 10 to 15 times that of Earth. These planets are composed of a solid or icy core surrounded by a thick, volatile, rich atmosphere, but their exact atmospheric composition is still shrouded in mystery. Despite their relatively low density, which suggests a significant amount of gas or volatiles in their atmosphere, determining the precise structure of these envelopes has proven difficult. Many mini-Neptunes are found in close orbits around their stars, where the heat causes their atmospheres to undergo chemical changes. Some may retain primordial hydrogen and helium atmospheres, while others could have developed secondary atmospheres through volcanic activity or the evaporation of surface volatiles. Observations from the Kepler and TESS missions show that mini-Neptunes are particularly common around Mort dwarfs and K-type stars. These stars have a habit of pulling planets into shorter orbits, which leads to higher equilibrium temperatures and dynamic atmospheric conditions. The biggest challenge in studying these planets is characterizing their atmospheres. Given their intermediate size, they fall into a gray area between gas giants and volatile-rich planets. Spectroscopic observations from telescopes like Hubble and JWST have often shown featureless spectra, likely due to high-altitude clouds or hazes. These aerosols obscure the absorption features of molecules, making it difficult to discern the exact atmospheric composition. A prime example of this difficulty is the planet GJ 1214b. Despite repeated observations, its spectrum lacks clear absorption bands, suggesting that it has a thick cloud cover or a high molecular weight atmosphere. Theories suggest that the atmosphere could be shaped by photochemical haze, condensation clouds, or equilibrium chemistry, each presenting unique compositional and dynamic challenges. Understanding how mini-Neptunes form is complex. Some models propose that they form beyond the snow line, the region in a protoplanetary disk where volatile compounds like water freeze and migrate inward, keeping a substantial amount of volatile material in their atmosphere. Others may have lost part of their original atmosphere due to photoevaporation, leaving them with thinner, denser atmospheres. This process is supported by the observation of a photoevaporation valley in the distribution of planet radii, which separates mini-Neptunes from super-Earths. The relationship between mass and metallicity is crucial when studying mini-Neptunes. Larger planets tend to retain lighter gases, while smaller planets are more likely to have denser compositions. The metallicity also plays a significant role in atmospheric opacity and chemical equilibrium, which affects our ability to observe these planets. Additionally, the planet's migration during its formation adds another layer of complexity to how its atmosphere might have evolved. The composition of clouds in mini-Neptunes may include various materials like silicate particles, sulfide condensates, or photochemical foldins, all of which affect the scattering and absorption of light, making it harder to distinguish between high metallicity atmospheres and cloudy ones. To truly understand these planets, high-resolution spectroscopy across multiple wavelengths is necessary, allowing us to probe deeper into the atmosphere and detect the presence of key molecules that might otherwise be hidden by clouds. One of the biggest obstacles in studying mini-Neptunes is their complex atmospheric structures. In many cases, the clouds or hazes that surround these planets make it difficult to determine the exact composition of their atmospheres. However, advancements in infrared observations, particularly from JWST, could help us explore beneath the cloud layers and reveal the presence of key molecules that are crucial for understanding the planet's potential habitability. The atmospheric dynamics of mini-Neptunes are shaped by factors like vertical mixing, temperature gradients, and photochemical processes. Phase curves and secondary eclipse measurements are particularly valuable in helping to understand heat distribution and circulation within their atmospheres. Without direct temperature measurements, scientists must rely on models based on assumptions about the planet's stellar flux and radiative transfer. At the same time, the long-term evolution of mini-Neptunes could be influenced by atmospheric escape. For those planets in close orbits to their stars, ultraviolet radiation can cause hydrodynamic outflows, stripping away the upper layers of the atmosphere over time. Some observations show signs of hydrogen and helium tails, which support this theory of atmospheric loss. This erosion could ultimately leave behind a rocky core, a transformation that could change the planet's potential for habitability. Hot Jupiters are another intriguing class of exoplanets. These gas giants orbit extremely close to their stars, often within 0.05 astronomical units, and have orbital periods of less than 10 days. Due to their proximity to their host stars, they experience extreme temperatures, but their size can still be inflated because of weak gravitational compression and stellar heating. The existence of hot Jupiters was a game-changer in our understanding of planetary formation. The discovery of 51 Pegasi b, the first exoplanet found orbiting a sun-like star, challenged the conventional wisdom that giant planets form far from their stars. Instead, it suggested that these planets must undergo inward migration after formation, likely due to gravitational interactions with the protoplanetary disk or other bodies in the system. Hot Jupiters exhibit tidal locking, meaning one side of the planet always faces the star, leading to extreme temperature differences between the day and night sides. This creates unique atmospheric dynamics, with strong heat redistribution and chemical distribution. Data from missions like Spitzer and JWST has revealed temperature variations across the planet, showing equatorial jets and heat transport efficiency. Some hot Jupiters display poor heat distribution, creating stark temperature contrasts. The atmospheres of hot Jupiters are mostly composed of hydrogen and helium, but many also show evidence of water vapor, carbon monoxide, and metal oxides. Using high-resolution spectroscopy, scientists have detected molecules like sodium, potassium, and even titanium oxide in the upper atmosphere of these planets. These compounds can influence radiative transfer and lead to thermal inversions, where the upper atmosphere is hotter than the layers below, affecting the planet's emission spectra. Clouds and hazes in hot Jupiters are made of silicates, sulfides, and iron condensates. These particles obscure the spectral lines, making it harder to analyze the composition of the atmosphere. By observing these planets across a broad range of wavelengths, researchers can determine whether the atmosphere is clear or cloudy. Some hot Jupiters, such as WASP 121b, show signs of complex vertical structure and metal enrichment, adding another layer of complexity to their atmospheric analysis. Atmospheric escape is a significant process in hot Jupiters, especially due to their high irradiation. Ultraviolet radiation from the host star can drive hydrodynamic outflows, stripping the planet of its hydrogen and helium and leading to extended atmospheres. This process not only affects the planet's size but also its long-term habitability potential. Some hot Jupiters like HD 209458b have been seen with hydrogen tails escaping into space. These escaping gases help us understand how much mass these planets are losing and how long they might last, especially for those close to their host stars. The inflated size of many hot Jupiters is still an area of active research. Some possible explanations include heating caused by magnetic interactions, tidal forces, and inefficient cooling from radiation. Not every hot Jupiter shows inflation, which suggests there are different internal and external factors at play. Scientists use observational data to improve thermal evolution models and investigate how different types of planets behave. In general, hot Jupiters have low orbital eccentricities due to tidal forces that smooth out their orbits. However, some show slight eccentricities, indicating they might be undergoing dynamic interactions, such as those caused by the gravitational pull of other planets or scattering events. Precision measurements of radial velocity and transit timing help us detect and model these orbital changes. Many hot Jupiters pass in front of bright stars, making them prime candidates for detailed atmospheric studies. Their deep transits and large-scale heights allow for better measurement of transmission and emission spectra. These planets are some of the best-known exoplanets and are key to calibrating instruments like JWST, Hubble, and ground-based telescopes. However, hot Jupiters are less likely to have moons or rings, as the strong tidal forces limit their ability to form these features. Still, some of them show unusual transit light curves, which could suggest that extended atmospheric features or material is escaping from the planet. Scientists study these light curve variations to learn more about mass loss and how the atmosphere behaves outside the planet's boundary. While hot Jupiters may not support life as we know it, they provide essential data on atmospheric physics, energy processes, and how planets interact with their stars. These gas giants are excellent testing grounds for studying cloud formation theories and understanding planetary evolution under extreme conditions. They've taught us a lot about exoplanet atmospheres, especially with their large signals, frequent transits, and diverse compositions. These attributes continue to make hot Jupiters a focal point for observational campaigns and atmospheric modeling studies. Some exoplanets have incredibly long rotational periods, meaning their days could last longer than their years. This happens because the planet's rotation has become synchronized with its orbit, a phenomenon known as tidal locking. In extreme cases, one hemisphere of the planet is always facing its star, while the other remains in darkness. This setup is commonly found in planets close to their stars, especially around maid-dwarf stars. Tidal locking has significant effects on the planet's climate, weather, and its potential for habitability. Tidal locking occurs when the planet's rotation slows down due to gravitational interactions over long periods. As the planet's rotation slows, internal friction releases energy, leading to a stable locked state. This process varies depending on the planet's size, orbit, and internal structure. For planets with short orbits, tidal locking can occur relatively quickly, sometimes within just a few million years. Many exoplanets in the habitable zone around red dwarfs are expected to be tidally locked as a result. These tidally locked planets develop unique atmospheric patterns. Climate models predict that a strong convection cell will form on the day side, where warm air rises and moves toward the night side at higher altitudes. Cooler air then sinks on the night side and flows back toward the surface, completing a circulation loop. This helps redistribute heat and prevent extreme temperature differences, but the efficiency of this heat redistribution depends on factors like atmospheric density and composition. Thermal observations and light curves have shown support for these models. Some tidally locked hot Jupiters have large day-night temperature differences, while others demonstrate effective heat redistribution. On planets with extremely slow rotation, Coriolis forces are weaker, leading to more symmetrical large-scale wind patterns. This affects cloud formation, precipitation, and the distribution of heat across the surface or oceans. High-resolution 3D climate models are being used to simulate these scenarios and predict what these planets would look like from an observational standpoint. The boundary between the day and night sides, known as the terminator, is where the most temperate conditions might exist. In some cases, light in this region could allow for processes similar to photosynthesis. However, energy in this area would be limited by the continuous but diffuse light. Some tidally locked planets, especially those with thin atmospheres, may face the risk of atmospheric collapse on the night side. Without effective heat transport, gases like CO2 may freeze and deplete the atmosphere over time. A thicker atmosphere or active geothermal heating could prevent this collapse. Understanding the minimum pressure needed to keep an atmosphere stable is key in determining a planet's potential for habitability. If oceans are present, they could help stabilize the climate by absorbing and redistributing heat through currents. However, if a planet is entirely ocean-covered, tidal locking could create strong equatorial jets that alter climate patterns. The complex interaction between ocean currents and atmospheric conditions continues to be a topic of research. For planets with slow rotation, their magnetic fields can also be affected. According to dynamo theory, weak rotational shear might reduce the strength of the planet's magnetic field. Without a strong magnetic field, the planet becomes more vulnerable to the stripping effects of stellar wind, especially around active near-dwarf stars. This adds another layer of complexity when studying these planets' long-term habitability and stability. Confirming rotation periods in exoplanets is difficult. However, methods like measuring phase curve shifts, Doppler broadening of atmospheric lines, and polarization signatures can help. These techniques are typically only applicable to transiting hot planets with favorable viewing angles. Future instruments will likely improve our ability to measure rotation rates for smaller, cooler planets as well. Some planets in eccentric orbits may experience a phenomenon known as pseudo-synchronous rotation, where the planet's rotation matches its orbital period at periastron. This leads to periodic, asymmetric day-night cycles that create complex climates. These planets, especially those in the outer habitable zone, offer valuable insights into exotic climate systems and rotational dynamics. In total, exoplanets with very long days provide a unique opportunity to study planetary climates and rotation. Their behavior often deviates from Earth-like models, requiring new atmospheric frameworks and modeling techniques. Continued research and infrared observations will deepen our understanding of how such planets maintain thermal stability and what kind of environments they might support. Some exoplanets are losing their atmospheres due to intense radiation from their host stars. This phenomenon, known as atmospheric escape, occurs when the upper atmosphere of the planet is heated by ultraviolet and X-ray radiation. The heat causes the atmosphere to expand and escape into space, potentially stripping away the planet's outer layers. This process is most common in planets that orbit very close to their stars. HD 209458b, a well-known hot Jupiter, is an example of this. Its extended hydrogen envelope, detected in ultraviolet observations, shows evidence of outflow velocities that exceed the planet's escape velocity. Follow-up observations of other systems have shown similar signs of atmospheric escape, such as helium escape detected in the near-infrared spectrum. These findings confirm that atmospheric loss is a widespread phenomenon. Smaller planets, especially those with thin hydrogen atmospheres, are more vulnerable to this type of escape. Sub-Neptunes and super-Earths, which are low in mass, can lose significant portions of their atmospheres over time. This process is thought to explain the observed radius gap, a region in the distribution of exoplanet sizes, where planets between 1.5 and 2 Earth radii are absent. Extreme cases of atmospheric escape can be seen in ultra-short period planets, which orbit their stars in less than 1 day. Some of these planets display comet-like tails made of gas and dust. For example, KIC 1255754-8b shows variable transit depths and asymmetric light curves, indicating material is being lost at a rapid rate. These planets may lose enough mass to significantly shrink in size over just a few million years, offering a glimpse into the final stages of planetary evolution. Instruments like Hubble, JWST, and ground-based spectrographs track absorption lines across various wavelengths. Atmospheric escape not only changes a planet's structure, but also its composition. A planet losing lighter elements may become richer in heavier molecules like water vapor or CO2. This chemical change affects surface pressure, temperature, and habitability. It can also cause unusual atmospheric chemistry, deviating from expected equilibrium. Stellar activity is key in determining escape rates. Active stars emit more UV and X-ray radiation, heating up and expanding the atmosphere. Flares and coronal mass ejections can trigger sudden increases in atmospheric loss. Long-term monitoring of stellar radiation is crucial for estimating mass loss over billions of years, especially for REM dwarfs, which remain active for long periods. Tidal forces can further enhance mass loss by weakening the gravitational hold on the atmosphere. Planets near the Roche limit may experience mass loss due to gas escaping directly to the star, as seen in WASP 12b, where metal absorption and orbital decay suggest mass transfer. These interactions affect stellar metallicity and the planet's orbital evolution. Some models predict that after a planet loses its atmosphere, it may leave behind a rocky core, known as a Chthonian planet. This theory may explain some close-in rocky planets that lack thick atmospheres. Determining if these planets formed as bare rocks or once had thick atmospheres requires modeling their composition, age, and stellar history. Future missions will expand our knowledge of evaporating planets. UV and infrared spectroscopy will discover new candidates and measure escape rates. Numerical models will refine predictions for different planets and stars, helping us understand atmospheric retention and loss. Atmospheric evaporation plays a key role in the evolution of exoplanets, affecting their mass, radius, chemistry, and potential for life. Ongoing observational campaigns are deepening our understanding of planetary evolution under extreme conditions. Some exoplanets face extreme weather that doesn't exist in our solar system. HD1 89733b, a hot Jupiter, experiences fierce weather, possibly raining molten glass sideways in hurricane-force winds. This planet orbits very close to its star, with a daytime temperature over 1,200 degrees Celsius. Observations from Hubble and Spitzer have detected cloud particles, haze, and chemical signatures linked to silicates, indicating an atmosphere shaped by intense radiation and rapid dynamics. HD 189733b is about 64 light-years away in the Vulpecula constellation and completes an orbit in just 2.2 Earth days. It's tidally locked, meaning one hemisphere always faces the star, creating extreme temperature differences. Winds over 8,000 km per h move heat across the planet, carrying vaporized silicates, which can condense and fall as solid particles, possibly glass. Spectroscopic data show silicate grains in the atmosphere, which could form clouds of instatate or forsterite. These clouds form on the cooler side of the planet, and when they precipitate, they may rain down as abrasive particles. The winds are so fast that gases are transferred from the hot side to the cold side at supersonic speeds. This creates powerful jet streams and broad equatorial currents. The planet also shows signs of photochemistry due to intense UV radiation from its star. This radiation breaks molecules apart, forming hazes and possibly sulfur-based aerosols, which affect the planet's temperature. Observations of the upper atmosphere reveal varying absorption features in sodium and other metals, helping scientists estimate the planet's temperature and pressure profiles. Ionized species suggest interactions with stellar winds, possibly leading to magnetic tails or atmospheric escape. HD1 89733b has become a benchmark for studying exoplanet atmospheres. It was the first planet for which infrared brightness maps were made, helping to test circulation models. Although glass rain hasn't been directly observed, conditions like high temperature, condensation curves, and circulation patterns support its existence. Other exoplanets may have even stranger weather. For example, Bulbioseat 76b shows signs of iron condensation and metal droplet precipitation during the night. These diverse exoplanetary climates expand our understanding of atmospheric chemistry under extreme conditions. Temperature inversions could occur in these atmospheres, with hot upper layers and cooler lower layers, affecting energy transfer and emission spectra. JWST's infrared capabilities will help refine these models. While these extreme weather conditions aren't conducive to life, they are valuable for studying atmospheric physics. They test models of cloud formation, gas dynamics, and radiative balance. Observations from HD 189733b and similar planets provide experimental data for high-temperature chemistry and gas dynamics. Laboratory simulations are being conducted on Earth to replicate these conditions and validate predictions. These exoplanets show how diverse planetary atmospheres can be, with extreme weather and unusual chemistry driven by proximity to their stars, tidal locking, and high radiation. Exoplanetary systems often feature multiple planets orbiting a single star, often in tight, compact configurations. These systems, like TRAPPIST-1 and Kepler-11, offer insights into planetary formation, migration, and long-term stability. Unlike our solar system, these systems have planets packed closely together, with orbital resonances stabilizing their orbits. Resonances occur when planets' orbits are linked by gravitational forces, keeping them in a predictable relationship. Transit timing variations, TTVs, help scientists study these interactions by tracking small shifts in the expected times of transits. TTVs allow scientists to determine planetary masses, eccentricities, and inclinations without relying only on radial velocity data. The Kepler-11 system includes 6 planets with orbital periods between 10 and 118 days. These planets have nearly circular orbits and low eccentricities, suggesting a calm dynamical history. Kepler-11 serves as a benchmark for studying compact planetary systems and their interior structures. TRAPPIST-1, Another well-known system has 7 Earth-sized planets in orbital resonance. Their orbits form a near-commensurate sequence with mutual gravitational interactions stabilizing the system over time. Numerical simulations confirm the system's stability, even over billions of years. Some systems, however, experience chaotic behavior, such as orbital instability or planet scattering. These dynamics can disrupt planetary orbits, alter climates, or even eject planets from the system. N-body simulations are used to study these effects and predict stable planetary configurations. Compact systems challenge traditional models of planet formation. While gas giants are thought to form farther from their stars, compact systems often have large planets close to their stars. One explanation is that these planets migrated inward through the protoplanetary disk, interacting with the gas and spiraling closer to the star. In multi-planet systems, the spacing between planets often follows regular patterns known as Titius-Bode laws. Although their physical origin is still debated, these patterns help guide planet searches and offer testable predictions. Deviations from regular spacing could indicate past collisions or orbital instability. Systems with low mutual inclinations allow for more transiting planets to be observed, which are more likely to be discovered in transit surveys like Kepler and TESS. Planetary compositions vary within a system. Some systems have a mix of rocky, volatile-rich and gas-dominated planets, even with similar sizes and orbits. These differences may result from variations in formation zones, migration paths, or atmospheric loss histories. Studying these contrasts helps refine models of planetary evolution under different conditions. Stellar properties also affect system stability. Metal-rich stars tend to host more massive, tightly packed planets. Stellar mass, rotation, and magnetic activity influence disk dispersal and planetary migration rates. The relationship between stellar characteristics and planetary configuration is an ongoing area of study. KE 8462852, or Tabby's star, gained attention for its irregular dimming events. Unlike regular planetary transits, the dimming here was unpredictable. Hypotheses range from stellar variability to dust clouds and planetary debris. A popular but speculative idea was that an artificial megastructure, like a Dyson swarm, might be responsible. However, further study indicated natural explanations were more likely, with dust clouds or comet-like debris around the star. The star is an F-type main sequence star about 1,470 light-years away. It shows no signs of pulsation or magnetic activity. The dimming is likely caused by material in the line of sight, not from the star itself. Polarimetric and spectrophotometric observations continue to refine models, with the possibility of discovering irregular cold dust structures around the star. SETI's searches for radio signals and laser pulses haven't found any evidence of artificial transmissions. While the idea of a megastructure was ruled out, it showed the importance of keeping an open mind when dealing with unusual data. The scientific process stayed strong, with ideas being tested and refined as new information came in. Another possibility is that interstellar dust or objects unrelated to the star might be causing the dimming. However, this is less likely because the star's brightness changes seem to be part of the system itself. If the dimming was caused by clouds in front of the star, other stars along the same line of sight would show similar effects. The data suggests that the material causing the dimming is within the KIC 8462852 system. Ongoing monitoring shows that the dimming is a slow process combined with sudden drops in brightness, supporting the idea of evolving dust clouds. One idea is that a disintegrating exomoon or migrating planetesimal belt could be causing the dimming, and future observations could test this. The unusual behavior of Tabby's star led to the creation of new tools for analyzing light curves, and it involved citizen science. Volunteers first noticed the strange signal in the Planet Hunters project, showing the value of human pattern recognition alongside automated data analysis. This discovery sparked public interest in exoplanet research. KC 8462852 has helped advance time domain astronomy, which studies objects that change over time. It also showed the limits of static models, stressing the need for long-term multi-wavelength observations. The star is an outlier compared to other Kepler stars, making it scientifically intriguing. While no clear cause for the dimming has been found, the evidence leans towards natural processes involving fine dust particles in orbit around the star. Carbon-rich planets are a hypothesized class of exoplanets with more carbon than silicates or oxides in their composition. 55 Canetii is a well-studied candidate, a super-Earth about 41 light-years away. With a mass 8 times that of Earth, its density suggests a solid composition. Early models proposed it could be rich in carbon, even possibly containing diamonds. These ideas come from studies of planet formation in disks, with more carbon than oxygen. In such environments, carbon compounds like silicon carbide might dominate. The 55 Canetii has an extremely short orbit of just 18 hours, likely making it tidally locked. Its dayside temperature exceeds 2,400 Kelvin, which is hotter than molten lava. While this intense heat makes stable surface solids unlikely, models still support the idea of a dense, carbon-rich interior. Infrared data from Spitzer and Hubble shows changes in brightness, indicating volcanic activity or surface changes. These surface processes, combined with its proximity to the star, make it hard to determine the exact composition, but carbon-rich models still seem to fit. Atmospheric studies haven't found a thick hydrogen or helium atmosphere, ruling out a mini Neptune. Spectroscopic data suggest a high metallic, high-pressure environment. If the planet lacks a significant atmosphere, the surface and interior compositions will dominate its signature, which would allow carbon chemistry to shape its thermal and structural properties. Diamond formation in the planet's interior could occur under high pressure and carbon-rich conditions. If the pressure exceeds 100 GPa, graphite could turn into diamond. While it's not directly confirmed, seismic and lab models support the possibility of diamond-rich mantles in such planets. An alternative theory is that 55 Canetii could have a silicate planet with a carbon-rich surface layer, possibly due to chemical variations or late-stage accretion of volatile materials. Future missions could help distinguish between these ideas by refining density measurements and analyzing surface composition. Carbon-rich planets might also form around stars with high carbon levels or low oxygen content. These stars could produce disks with altered solid compositions, making carbon-rich planets more likely. Surveys of host star compositions are being conducted using data from telescopes like Gaia. The concept of carbon planets has interesting implications for geology. Diamond-rich mantles could behave differently from regular planets, affecting tectonics and magnetic fields. The surface composition would influence reflectivity, temperature regulation, and chemical weathering. Understanding these processes helps expand our knowledge of exoplanet diversity. 55 Canetii experiences intense irradiation, likely preventing a stable surface. However, deeper layers may remain shielded from stellar heat, preserving high-pressure phases like diamond or carbide. Over time, volatile loss may lead to a metal-rich and carbon-enriched core, providing insight into the evolution of similar planets. Future missions like JWST and Ariel could improve atmospheric models and detect secondary atmospheric components. High-precision mass-radius measurements might reveal changes in composition for planets near twice Earth's radius. Lab studies of carbon-rich materials under extreme conditions will also help interpret the data. In conclusion, carbon-rich planets like 55 Canetii represent a fascinating part of planetary diversity. Although direct evidence of diamond interiors is not yet possible, current models and data suggest that these planets could be carbon-dominated. They challenge our understanding of how chemistry shapes planet formation and structure across the galaxy. Climate modeling for exoplanets involves adapting Earth-based techniques to different planetary conditions. These models predict temperature, wind, and cloud patterns using data on the planet's size, atmosphere, orbit, and rotation. The goal is to forecast surface conditions and the potential for habitability. Climate models are particularly important for understanding tidally locked exoplanets, which have one side always facing the star. General circulation models, GCMs, simulate climate across different latitudes, longitudes, and altitudes, accounting for heat transport and seasonal changes. Simplified models are used for planets with unknown parameters. For tidally locked planets, GCMs show how heat can be distributed between the star-facing side and the dark side, preventing atmospheric collapse. Cloud formation on the star-facing side increases reflectivity, which affects surface temperatures. Different stars emit different spectra, affecting how energy is absorbed in a planet's atmosphere. Male dwarfs, for example, emit mainly infrared light, which interacts differently with greenhouse gases compared to sunlight. This changes temperature predictions and habitability assessments. WIZARD changes temperature predictions and habitability assessments. Planetary albedo, or reflectivity, is a key factor in regulating temperature. Climate models take into account clouds, surface reflectivity, and ice coverage. On planets with dynamic clouds, feedback loops can either stabilize or destabilize the climate. Water-rich planets may exhibit self-regulating thermostat effects, but these depend on surface and atmospheric conditions, which are still not fully understood. Climate models also consider extreme scenarios like the runaway greenhouse effect, where water vapor traps heat and raises temperatures, or snowball Earth, where ice reflects too much sunlight, causing cooling. These models help define the boundaries of the habitable zone. Axial tilt, or obquity, affects how energy is distributed across a planet. Planets with high obquity have extreme seasonal changes, while those with zero tilt experience constant heating at the equator. Climate models simulate how these variations influence habitability and circulation. The planet's atmosphere plays a huge role in climate. Thick CO2 atmospheres cause strong greenhouse effects, while thin atmospheres lead to rapid heat loss. Water vapor and methane are especially important due to their ability to trap heat. Climate models explore different atmospheric compositions to see which combinations could support liquid water on the surface. Ocean models are used for water-rich planets. Holt's oceans store heat and redistribute it, helping to stabilize temperatures. However, if a planet is entirely covered by water, nutrient cycling and vertical mixing become important for long-term stability. Most ocean models for exoplanets are simplified, but comparisons with Earth's climate history help validate them. Observational data, such as transit spectra and brightness temperatures, are used to refine climate models. These models help predict surface conditions and habitability, offering insights into the climates of distant worlds. In short, climate modeling helps scientists understand exoplanets. It turns limited data into detailed predictions about habitability, atmospheric stability, and climate. As instruments improve, these models will continue to provide more insights into distant planets. The shape and strength of certain features tell us about temperature, pressure, and composition. Spectral data is adjusted for errors caused by stars, instruments, and other factors. Stars often have spots, flares, and other features that can hide or mimic signals from planets. To deal with these, we observe the star in different bands and use careful models to account for these effects. Techniques like differential spectroscopy and principal component analysis help focus on the planet's signal. We also use secondary eclipse spectroscopy, which occurs when the planet moves behind the star. This lets us measure the planet's heat or reflected light. By comparing emission and transmission spectra, scientists can learn about the planet's temperature and atmospheric structure. Phase curve measurements track the planet's brightness throughout its orbit, revealing heat distribution and possible cloud or atmospheric circulation. Changes in these curves can show changing weather patterns. Together with transit data, phase curves give us a full view of the planet's climate system. Transit spectroscopy can detect clouds and hazes, which may hide certain spectral features. For example, if the spectrum is flat, it may mean high-altitude clouds are blocking molecular signals. The composition and placement of clouds affect how we see the lower atmosphere. Identifying and understanding clouds is essential for interpreting spectra correctly. The resolution and wavelength coverage are key to detecting different molecules. JWST, for example, can detect water, CO2, methane, and other gases from 0.6 to 28 microns. Higher resolution shows finer details like wind speed and altitude. Ground-based telescopes like HARPS and ESPRESSO also help by measuring radial velocities and absorption lines. This method works best for short-period planets that transit frequently, allowing for multiple observations. For longer period planets, more patience and long-term planning are needed. Bright stars are preferred because they provide more light, improving the data quality. When choosing targets, scientists consider factors like the planet's size, orbit, and the brightness of its star. Algorithms are used to convert observed data into models of the planet's atmosphere. These models compare the data to theoretical spectra based on simulations. Machine learning techniques are also used to estimate things like gas amounts, cloud properties, and temperature. However, these models must consider that many different factors could produce the same results. Transit spectroscopy is only useful for systems where the planet's orbit allows us to see it cross in front of its star. For planets that don't transit from our perspective, we need different methods like direct imaging or high dispersion spectroscopy. Despite these limitations, transit spectroscopy has been a game changer for studying exoplanet atmospheres. It provides detailed chemical and thermal information using only the star's light and geometry. As technology improves, this technique will continue to drive discoveries about exoplanet climates, composition, and habitability. Brown dwarfs are objects with a mass between the heaviest gas giants and the lightest stars. They can't sustain hydrogen fusion like stars, but they can briefly fuse elements like deuterium or lithium. This makes them hard to classify, as they're too massive to be planets and too small to be true stars. Brown dwarfs have helped scientists refine how we detect and classify celestial bodies. The 13 Jupiter mass limit is often used to distinguish brown dwarfs from planets, but this limit isn't perfect. Some objects below this threshold may form like stars, while others above it may form in protoplanetary disks. Brown dwarfs can orbit stars or exist alone in space. When they orbit close to stars, they can mimic planets in observations, such as radial velocity or transit data. Objects between 13 and 30 Jupiter masses are especially hard to distinguish from hot Jupiters. Spectroscopy and astrometry are often used to resolve their nature. These objects complicate studies of exoplanet populations. Unlike planets, brown dwarfs cool over time. They start hot but gradually lose their heat, and their spectra shift from visible to infrared wavelengths. This cooling process helps distinguish them from gas giants, which maintain their heat due to their star's proximity. Brown dwarfs are often found through direct imaging, especially in wide orbits or as free-floating objects. Surveys like 2MASS and WISE have found many brown dwarfs in our neighborhood. Sometimes they're mistaken for exoplanets because of their size and temperature. By measuring motion, brightness, and spectra, we can figure out whether an object is a brown dwarf or a low-mass star. Some brown dwarfs show weather patterns similar to giant exoplanets, including clouds, atmospheric circulation, and variable light curves. Studying these brown dwarfs helps validate models used for distant exoplanet atmospheres. Brown dwarfs are also known to have planetary systems of their own, which offer insight into planet formation in different conditions such as cooler temperatures and weaker radiation fields. The brown dwarf desert refers to the rarity of brown dwarfs close to stars. While giant planets and stars are common in this range, brown dwarfs are not. This may reflect differences in their formation or migration history. Studying this desert helps scientists understand how planets and stars interact in a system. The difference between brown dwarfs and planets often depends on how they formed. Planets typically form through accretion in a disk, while brown dwarfs form from gravitational collapse of a gas cloud. However, it's hard to determine the formation history directly. Scientists often rely on indirect clues such as the presence of a debris disk or orbital separation. Some free-floating objects are hard to classify, as they may have been ejected from planetary systems or formed on their own. These objects blur the line between brown dwarfs and planets. The study of brown dwarfs helps scientists understand both planetary and stellar evolution. Their atmospheres contain complex chemistry, including methane, ammonia, and alkali metals. By studying their internal structure and behavior, scientists can learn about the transition between planets and stars. Brown dwarfs can also have their own planetary systems, offering a chance to study planet formation in unusual conditions. While rare, the detection of planets around brown dwarfs shows that planet formation is a common process. In summary, brown dwarfs sit in a critical zone between planets and stars. They challenge our traditional understanding of these objects, and studying them helps refine how we classify and understand the diversity of substellar bodies. Stellar metallicity, or the amount of heavy elements in a star, plays a big role in the types of planets that form around it. Stars with more metals tend to have larger and more planets, especially gas giants. This supports the idea that planets form by gathering solid material in a disk. Stars with higher metallicity likely have disks full of raw material, making it easier for gas giants to form. This explains why gas giants are more common around metal-rich stars. For smaller, rocky planets, metallicity is less important. These planets can form even in low metal environments. This difference suggests that while metallicity affects the chance of forming large planets, it's less crucial for smaller ones. Metal-rich stars are more likely to have close-in giant planets or hot Jupiters, while stars with lower metallicity are more likely to have multi-planet systems with smaller Earth-like planets. This shows that metallicity affects how planets form, but it doesn't determine their final position or size in a system. Recent studies look at specific element ratios, like carbon to oxygen or magnesium to silicon, to help predict the composition of planets. These studies refine our understanding of planet formation. For example, a high carbon to oxygen ratio might favor carbon-rich planets, while a high magnesium to silicon ratio could influence a planet's mantle composition. Stars with higher alpha elements like oxygen and magnesium might form different planetary systems than stars rich in iron. These patterns reveal how the galaxy's chemistry has evolved over time. Older stars, for example, tend to have more alpha elements but less iron. The relationship between stellar metallicity and planet formation is complex. Metal-rich stars are more likely to have giant planets, while rocky planets form in a wider range of metallicities. However, factors like stellar composition, migration, and disk dynamics also play major roles. Studies of large data sets from TESS and Kepler continue to shed light on how metallicity affects planet formation. Metal-rich stars are more common in the galactic disk, where most planet searches happen. In metal-poor regions like the galactic halo, fewer planets are found. However, a few planets, like one around a pulsar in the M4 cluster, show that planets can form in extreme environments. Metallicity affects planet formation and how we observe stars. Metal-rich stars are brighter and easier to study, which can impact detection statistics. Future missions will improve measurements and help refine our understanding of how stars influence planets. In short, stellar metallicity plays a big role in planet formation, size, and composition. Some planets have retrograde orbits, meaning they orbit in the opposite direction of their star's rotation. This suggests that something changed their orbit after they formed. Retrograde orbits are common in hot Jupiters, which likely formed farther from their star and then moved inward. Retrograde motion may happen due to interactions with companion stars or other planets. Tidal forces can eventually circularize these orbits. Cooler stars tend to have aligned orbits, while hotter stars show more misaligned or retrograde orbits. Retrograde planets challenge the idea that planets always form in aligned orbits. They suggest that dynamic changes after formation are common, especially in systems with multiple large planets. Circumbinary planets orbit both stars in a binary system, like those in the Kepler 16 and 47 systems. These planets can have stable orbits if they're far enough from the stars. Planets in binary systems are more common and easier to detect, though close binaries can disrupt planet formation. Planet formation in multi-star systems depends on how the star's disks interact. Wide binaries are more likely to host planets, while close binaries may prevent it. Some planets have still formed in tight binaries. In these systems, gravitational interactions can affect planetary orbits. This helps explain unusual orbits like retrograde or highly inclined paths. Studying planets in binary systems helps us understand planet formation in complex environments. In conclusion, planets can form and remain stable in multi-star systems. Continued research will improve predictions for planet formation in these systems. Tidal forces change the shape of planets and stars, causing bulges that release energy. Over time, these forces can affect rotation, orbits, and spin alignment. The strength of tidal effects depends on mass, size, distance from the star, and internal structure. One common result is tidal locking, where a planet's rotation syncs with its orbit, creating permanent day and night sides. Tidal locking is common for close-in exoplanets, particularly those in red dwarf habitable zones. Such planets have strong temperature differences. The tides also cause orbital circularization, especially for planets with eccentric orbits. Over time, orbits become circular as internal friction releases energy. This is seen in hot Jupiters, which have low eccentricities despite initial irregularities. The rate of circularization depends on the planet's mass and its proximity to the star. In systems with multiple bodies, tidal heating is significant. For example, Jupiter's moon Io remains active due to tidal heating. Exoplanets in similar systems may have subsurface oceans or molten interiors. Tidal heating could be key to habitability on otherwise cold planets. Tidal forces also affect the planet's tilt or obquity. Strong tidal forces reduce the tilt, stabilizing the climate and seasons. Planets with high obquity may experience chaotic shifts before stabilizing. The rate of tidal change depends on the planet's internal dissipation, measured by the tidal quality factor. Gas giants have higher Q values, making them less responsive to tidal changes. Measuring Q is hard, but indirect methods help refine our understanding of planetary interiors. Tidal interactions can cause orbital decay, especially for planets close to their stars. As angular momentum is lost, orbits shrink, and planets spiral inward. Eventually, they may be destroyed by tidal disruption. This is expected for ultra-short period planets. Tides can also cause spin-orbit misalignment, or even reverse a planet's rotation. Observations suggest that tidal realignment is slow for massive stars, which helps improve models of star-planet interactions. Tides also affect exomoons and ring systems. Moons experience similar effects which may stabilize or destabilize their orbits. Tidal heating can sustain geological activity on large moons, potentially creating subsurface oceans. Detecting these moons is challenging, but tidal theory helps predict where they might be. Tidal dissipation may explain why some hot Jupiters appear larger than expected. Internal heating from tidal forces is a leading explanation, though other factors like kinetic energy transport could also play a role. Tidal effects influence planetary inflation, especially in gas giants. Some hot Jupiters are larger than expected for their mass, possibly due to tidal heating. Understanding this inflation is crucial for interpreting size measurements. Future missions will improve our understanding of tidal effects through better timing, phase curves, and long-term monitoring. Tidal evolution helps explain discrepancies in orbital distributions, especially for close-in planets. Numerical simulations test how tides interact with migration and resonance trapping. In general, tides shape exoplanets' orbital and rotational properties, affecting climate, habitability, and system structure. As detection techniques improve, more evidence of tidal effects will emerge, helping unify theories of exoplanet dynamics. Young exoplanets, typically less than 10 million years old, offer a unique opportunity to study planet formation. These planets are often still embedded in their host stars' protoplanetary disks and may show ongoing accretion, heating, and migration. Studying these planets helps test theoretical models against real data. These exoplanets are usually found in stellar nurseries like Taurus, Upper Scorpius, and the Orion Nebula. Infrared or radio observations are needed to detect them. Direct imaging is the best method for spotting young exoplanets because they are still hot from their formation. Unlike older planets, they emit thermal radiation, especially in infrared. This makes it easier to image giant planets that are far from their stars. Some young planets show signs of active accretion, such as excess ultraviolet or hydrogen alpha emissions. These signatures indicate ongoing material gathering from the surrounding disk. A well-studied example is PDS-7b, a planet still embedded in its natal disk. Observations show the planet carving out a gap in the disk, providing evidence for formation models. A second planet, PDS-7c, was discovered in the same system. Another example is AB Righi, where spiral structures and a potential planet have been imaged within the inner disk. Young exoplanets may have inflated radii, as they haven't yet contracted fully from their formation phase. Measuring mass and radius helps refine models of planetary evolution. Planetary atmospheres evolve quickly in the early stages, and young gas giants may still have hydrogen and helium envelopes that are vulnerable to photoevaporation. Observing mass loss from these planets helps refine theories on atmospheric escape, particularly for smaller planets. Young exoplanets often reside in multiple planet systems where gravitational interactions continue. These interactions can lead to migration, scattering, or resonance trapping. These events help researchers understand the diversity of mature systems. The biggest challenge in studying young exoplanets is noise from stellar activity, but multi-wavelength observations improve signal clarity. In conclusion, studying young exoplanets reveals the processes that shape all planetary systems, including our own. As technology improves, we will gain a better understanding of how planets form and evolve. Protoplanetary disks are rotating clouds of gas and dust around young stars where planets form. These disks last 1 to 10 million years and provide the material needed to create planets. The disks form when a molecular cloud collapses, creating a flattened disk. Initially rich in hydrogen, dust, and volatile compounds like water, these disks gradually evolve, with dust particles forming pebbles, planetesimals, and eventually planetary cores. Advanced telescopes like ULMA have helped study disks in detail, revealing features like rings and gaps that suggest the presence of forming planets. The composition of the disk influences what types of planets can form. For example, the snow line, where volatiles freeze into solids, helps determine where rocky planets, gas giants, and ice-rich bodies form. Dust particles collide and settle in the disk, leading to planetesimal formation. Gas dynamics in the disk, including turbulence and pressure gradients, also affect planet growth and migration. Disks have limited lifetimes due to photoevaporation and mass loss. If the disk disperses too quickly, gas giants may not form in time. The chemical composition of the disk, including ices and organics, influences the makeup of the planets and their atmospheres. Disks can also be misaligned, producing planets with tilted or retrograde orbits. These interactions challenge the assumption that planets always form in aligned orbits. As planets form, they interact with the disk, opening gaps or migrating inward, leaving observable signatures. Protoplanetary disks play a key role in planet formation, providing the material and environment for planetary systems to develop. Understanding these disks gives valuable insights into how planets are born and evolve. Artificial intelligence, AI, is now essential for detecting and classifying exoplanets. AI processes large data sets from space telescopes like Kepler, TESS, and Plato, helping identify potential planets more quickly and efficiently than traditional methods. Machine learning algorithms analyze light curves for periodic dips that indicate a transiting planet. AI can also help predict planetary parameters such as mass, radius, and orbital period. AI has made significant contributions, like the discovery of Kepler-90a, the 8th planet in an existing system, by reanalyzing Kepler data. AI also aids in analyzing transit timing variations, identifying additional planets in multi-planet systems. AI tools are flexible, allowing more accurate fitting of observed data. However, challenges include model interpretability and training bias. Efforts are underway to make AI more transparent and to avoid biases in training data. AI has become an indispensable tool in exoplanet research, improving discovery rates and providing new insights into planetary systems. As AI continues to advance, it will further expand our understanding of planets across the galaxy. Citizen science has also contributed to exoplanet discovery. Projects like Planet Hunters invite volunteers to help analyze light curves for potential transit signals. Humans can spot irregular patterns that AI might miss. Some volunteers have even discovered new planets like the unusual dimming behavior of Tabby's star. Citizen scientists have played a key role in discovering and confirming exoplanets, including planets like PH1b in a 4-star system. Platforms like Planet Hunters allow volunteers to inspect light curves for potential transit signals. Volunteers receive training, mark suspected transits, and classify features based on shape and timing. The results are aggregated, reducing individual error. Active volunteers may even co-author scientific papers. These projects help process large data sets that small teams couldn't handle alone, especially for identifying long-period planets or disintegrating exoplanets. Citizen science also aids in training AI for better detection. AI and citizen science work together to enhance exoplanet discovery. Promising candidates flagged by volunteers undergo further verification with telescopes. Planet Hunters has expanded to include tests for nearby bright stars, enabling faster follow-up. These platforms also promote science literacy and provide real research experience. By leveraging both human and machine strengths, citizen science is a vital part of exoplanet exploration. Gaia, the European Space Agency's mission, creates an accurate 3D map of stars. While not an exoplanet mission, Gaia helps refine the properties of known exoplanets by improving knowledge of their host stars. Its high-precision measurements of stellar distance, size, and temperature allow for more accurate exoplanet characterization. Gaia also detects the gravitational wobble of stars caused by orbiting planets, improving the detection of massive long-period exoplanets. Gaia data is crucial for refining the mass and orbital characteristics of planets. It resolves the true mass of planets detected through radial velocity by determining their orbital inclination. This is especially helpful in distinguishing planets from brown dwarfs or low-mass stars. Gaia also contributes to understanding system stability and formation by refining the positions and motions of stars in multi-planet systems. Gaia works in synergy with missions like TESS and JWST. TESS identifies exoplanets, Gaia provides host star data, and JWST analyzes atmospheric properties. Together, these missions form a comprehensive pipeline for exoplanet discovery and exploration. Gaia's continued data releases will further enhance our understanding of planetary systems and refine the exoplanet catalog. Future missions like LUVR aim to directly image Earth-like exoplanets and detect signs of life, taking exoplanet exploration to the next level. LUVR, a proposed mission, would use advanced coronagraphs or starshade devices to block out starlight, allowing direct imaging of faint orbiting planets. Unlike indirect methods like transit or radial velocity, direct imaging with LUVR could capture reflected light from planets, providing data on their surface conditions and potential for life. HABEX, a smaller mission, also aims to image Earth-like exoplanets with a dedicated starshade to block starlight and enable clear observations in visible light. These missions, part of the 2020 ASTRO 2020 Decadal Survey, will focus on biosignature detection. Another ambitious mission, Origins, would study protoplanetary disks and planet formation in the far infrared. Origins will complement LUVIR and JWST by detecting complex molecules like water and organics in early-stage disks. In the near term, telescopes like JWST will perform atmospheric spectroscopy of small exoplanets, while missions like Ariel will survey hot and warm exoplanet atmospheres. Ground-based telescopes like the 30-meter telescope and Giant Magellan Telescope (GMT) will enhance high-resolution spectroscopy and imaging, revealing surface features and weather patterns. These future missions will focus on detecting biosignatures such as oxygen, ozone, and methane in exoplanet atmospheres. New technologies, including advanced wavefront control and high-contrast imaging instruments, are essential for suppressing starlight and imaging Earth-like planets. Public and international collaboration will be key in making these billion-dollar missions successful. Missions like LUVR and HABEX represent the next frontier in exoplanet science, focusing not only on finding planets but understanding their habitability and searching for signs of life. The study of exoplanets has revolutionized our understanding of the universe. Before the discovery of exoplanets, the solar system was our only model for planetary science. Now, with thousands of exoplanets confirmed, astronomers can compare different worlds and challenge old assumptions about planet formation. Exoplanets also redefine habitability, with many planets lying in their stars' habitable zones, some with Earth-like characteristics. This expands the criteria for biosignature searches and broadens the concept of life-friendly environments. Data from missions like Kepler, TESS, and Gaia show that planetary systems are common, suggesting that planet formation occurs across various stellar environments. This suggests that our solar system is just one among billions. The study of exoplanets also highlights the importance of stellar context. Planetary properties are deeply connected to the characteristics of their stars, helping scientists understand which stars are most likely to host habitable planets. By combining methods like transit photometry, radial velocity, and direct imaging, scientists can build detailed planetary profiles, revealing information on a planet's size, mass, density, temperature, and sometimes its atmosphere. This enables comparative planetology, revealing the vast diversity of exoplanets from gas giants orbiting in ours to icy planets colder than Pluto. These findings challenge traditional classifications and help scientists focus on planets with liquid water, stable atmospheres, and signs of disequilibrium. Exoplanet research also impacts other scientific fields. Advances in photometry, adaptive optics, and machine learning developed for exoplanet detection are now applied in cosmology, stellar astrophysics, and more. Additionally, studying Earth-like exoplanets helps scientists understand Earth's climate, atmospheric chemistry, and geologic activity, broadening the scope of planetary science. The study of exoplanets has grown rapidly, evolving into a structured discipline with international collaboration. Each new mission builds on the foundations of previous ones, transforming astronomy into a science of systems, combining astrophysics, planetary science, chemistry, and biology. As discoveries accelerate with new tools like JWST and Plato, exoplanet research remains one of the most exciting and interdisciplinary frontiers in science.